Good morning, good afternoon, good evening to everyone, and welcome back to the second day of the fifth forum on Generative Edge AI. Ciao Roberto, welcome. Good to see you.
Ciao Danilo, hello everyone, nice to see you.
Today, so the day two, Roberto and myself will chair this session. So Roberto, we are going to have a lot of speakers today from real excellent people in the Edge AI Foundation, and we will dive a little bit deep on hardware and on platform resources, as well as some topics related to research. So we have different companies represented. So let me quickly remind: BrainChip, NXP, Godel Space, Murkek, Arduino, Alif Semiconductor, and Forest Hub.ai.
Yeah.
So what are your expectations for today, Roberto?
Yeah, quite exciting. I mean, after yesterday, more than 4 hours, as also you remarked at the end of day one, many different perspectives yesterday from also some optimization compiler and also very insightful discussion between Pete and Bill Curtis at the beginning. Today we are shifting a little bit, looking at the hardware optimization, as you mentioned, and also the system perspective that somehow we have observed a little bit also yesterday. Looking forward to hear about what comes next and also see the perspective. I think it was interesting to hear yesterday from Pete, for example, that we were having the first Generative AI Forum 2 years ago, more or less. It was end of March, and the big question was, what can we do? Is it really possible? Can we envision to have a Generative AI at the edge? And today we are talking about a completely different world. And yesterday we had some talk about physical AI and talking about scaling up these kind of systems at the edge to an hyperscale. So very exciting times, and I look forward to hear about what comes today.
Yeah, we are certainly moving in a period where generative Edge AI in the different agentic and physical embodiments represent the reality, and not just a wishful thinking or a hope for the future. And today my expectation is to learn more from the different speakers and get more understanding about what I'm believing, which essentially these topics are definitely blurring a little bit what was intended as a TinyML, further incorporating also these past techniques.
Yeah.
I leave the floor to you.
Yep.
You are the
Thanks,
chair
Danilo.
of the session today. I wish you a fruitful discussion. I will be back, obviously, for any need, and maybe we'll pose some questions from time to time.
Thanks a lot, Danilo. Thank you so much. Thanks. So we can then start with the first speaker, Ritik from BrainChip, who is going to give us a talk on running generative AI locally and open SSM model for edge devices. Thanks for joining this day 2 of the forum, Ritik. Feel free to share your presentation and start your talk. Thanks a lot.
Thank you for introducing Roberto. Just a second. Okay. Hello, everyone. I am Ritik Shrivastava, Solutions Architect at BrainChip. And today, as an active member of developer community, I'm super excited to talk about our state space model-based LLM we have been working on at BrainChip. We are opening up our 1.2 billion parameter SSM model to the community. So anyone can download it run it, fine-tune it, and deploy it on their edge devices. In this talk, we will cover why SSM-based models running on BrainChip accelerators are the future for generative AI on edge, and how you can engage with our reference model to explore the possibilities. Now, coming to what problem exactly we are addressing here by introducing this SSM-based model. So the biggest challenge for generative AI on edge is not compute, it's memory movement. It's kind of a well-known thing as of now for people working on Gen AI. This is where the transformer architecture struggles and where SSM have a fundamental advantage. Now, the AI compute has changed a lot. Before in CNNs, each parameter was involved in multiple computations. So networks were more compute bound. For generative AI using transformers or SSMs, each parameter generally corresponds to single computation, which means that with Gen AI, supplying data to the compute engine becomes the bigger problem than compute capacity itself. Now, ideally, storing all parameters on a chip, on an ASIC, storing all the parameters in SRAM would consume the least energy. But we can't have a large SRAM. It's just not practical because size also matters. So we rely on flash or DDR. Now, in case of transformers, you need to store weights, and with every incoming token, the growing KV cache requires a lot of writes. This basically conflicts with the flash technology and forces DDR, which here you can see on the left lower side, it consumes higher power per fetch. Now, SSMs are a bit different. They have a constant size state that doesn't change with new tokens. And since it's small, it can be stored in SRAM. And with no KV cache writes, weights can stay in flash. This helps you to reduce the memory movement and overall lowers the system power consumption. And this is what make generative AI practical within the power and memory limits of edge devices. And that's why BrainChip has been working on enabling efficient SSM processing on edge. Now, before we go deeper into the discussion, here's a quick snapshot of what BrainChip is and what we focus on. So we are worldwide leaders in neuromorphic AI on edge. The basis of SSM came around 2019 from the paper LMU, which talked about linear time invariant state space models. And BrainChip has been doing cutting edge research on SSMs around from like 2020, around the time when Stanford and CMU started working on that. Now, it has been adapted in mainstream industry also, but most of the industry and academia have been focusing on optimizing SSMs for GPU, but BrainChip has been working specifically on creating and optimizing SSM for edge. Now, our offerings focus across chips, IP, developer tools, and solutions. And the model which we are releasing today fits in the generative AI solution target. And this is the first time we are opening it up publicly. Now, I've been talking about SSMs a lot. So just to give a brief introduction of what exactly that is. So SSMs derive from control theory. These are basically recurrent models that can be trained like CNNs and deployed like RNN. Which means that while training, you can use the parallelizability of GPUs, but when you are deploying it for inference, you can run it like RNNs in a streaming mode. They have a constant size state that act as a brain, or you can say memory of the layer, and stores the context of previous tokens while processing for the next tokens. This gets you stable training in convolution domain and efficient inference in recurrent domain. It's a like known problem for especially recurrent models that they suffer to vanishing gradient problems. So SSMs do not suffer through that. And you can think of them like a generalized Fourier filter stacked with nonlinearities. Now, our implementation of this architecture is called TENS, and it is what powers our LLM model that we are releasing. Now, earlier we talked about why memory movement is the real bottleneck on Edge. So now let's see how exactly this actually plays out between transformers and SSMs. So on the left side, you see for transformers, each new token requires updating the KV cache, which grows with sequence length. This basically means that constant writes and reads, which creates heavy memory traffic and high power consumption, especially when off-chip DRAM is involved. Now, on the right side, you see SSMs. It's kind of a bit different from basically mainstream architectures. So they have a fixed size state that doesn't exactly expand with context, and this means that fewer memory transfers, no KV cache overhead, and has ability to keep weights in flash and state in SRAM. This helps you to dramatically lower energy use and better efficiency for edge devices. Now, there is also another element to it, which is compute bound. So for compute scaling difference, in general, transformers compute scales quadratically with context length, while SSM compute scales linearly. So the longer the context is, the bigger the efficiency gap is. And this is what makes SSMs the right fit for the edge hardware, because they provide constant memory, lower power, predictable scaling, and no matter how long the context gets. Okay, so now beyond the model itself, we have also been innovating around it to make real-world edge AI applications more practical. So let me share two of these with you. First is precog, which is our approach to RAG on edge specifically. So RAG, or retrieval augmented generation, retrieves relevant external information and combines it with the query to generate accurate answers. The biggest challenge there is that every query requires processing of retrieved document along with the query, which adds latency and also increased memory demand. Now, precog solves this by pre-computing hidden states for the context documents offline and storing them in a compact form. So when a query comes, we simply fetch the relevant hidden state and fuse it with the existing hidden states. Now, this makes the context ingestion instantaneous, which means time to first token is minimized and reduces the memory requirement too. And because this approach is super lightweight, it also enables RAG applications on edge devices like smart refrigerator system answering questions from its user manual, or just making intelligent interaction possible for any device in general. Now, the second second innovation which I want to talk about is our proprietary compression algorithm. So here we show the perplexity of the model, and just to give you some context, perplexity is almost like how much confused the model is while doing the next token prediction. So the lower the perplexity, better is the model performance. Now, here you can see that when it compresses the model to 4-bit with less than 1% accuracy loss, there is basically a reduction of memory by 8x without almost no loss in accuracy. Here on the right side, you see the table which shows a perplexity number on pile data set. The FP32 baseline is 6.35, and at 8-bit there is zero degradation. At 4-bit we see under 1% degradation. So you get 8x reduction in parameter storage and data transfer with model quality fully intact. Now, putting everything what we have covered together, the same parameter count, transformers and SSM look very different on edge hardware. Transformers at this size have KV cache growing with context length, has unpredictable memory spikes, quadratic attention per token, and high power from memory movement. For SSM on the right side, you have no KV cache, flat memory at any context length, and linear inference, much lower memory movement, which basically means much lower power consumption. Both have same parameter count, but fundamentally different hardware profile. And this is what makes real-time generative AI practical within the power and memory limits of edge devices. Now, this brings us to what we are releasing today. We are releasing our, as we discussed, our TENS 1.2 billion parameter LLM reference model, so you can start experimenting with it and see the potential. You can check out this GitHub link, which has been mentioned on the slide. Now, as you can see on the left-hand side, we are giving access today to the LLM model and its weights, along with the documentation that describes the model, an example of how to run inference with a custom prompt. This is a good starting point to start experimenting with it right away. On the right, you see that there are 4 more pieces rolling out shortly. First is our TENS Python package, the full model architecture, installable via pip, so you can start building with it. Second is the evaluation script, a single command to benchmark the model on standard data set, so you can compare it against the other available models. Third is the fine-tuning script, so you can adapt the model to your own data and use case. And finally, the deployment pipeline, which converts the model to optimized binaries and helps you to deploy it on your target device. Now, rest of the tooling will be available in coming weeks, and we will keep the community posted as each piece lands. Now, when we release, when the full release is out, here is what it unlocks for you. For ML engineers, you will be able to benchmark the model head-to-head against other open source small language models, fine-tune for your domain and using our scripts, and test on your own data sets if you have some internal data sets. So you can do that too. For hardware and silicon engineers, you'll be able to measure tokens per second, memory, and power on your own target hardware. You can also profile the constant state inference and see how it behaves without KV cache scaling, and benchmark it against transformer baseline on your silicon. For product managers, you will be able to run the benchmarks to understand model capability firsthand, evaluate the real world performance on your domain data, and decide whether if SSMs fit on your edge product roadmap or not, which is like super exciting. Now, the end-to-end developer workflow will mostly look like you can clone the repo, evaluate the model, you can fine-tune it on your own personal data set if you want to. You can have some domain-specific data sets, which you can fine-tune to, convert it to binary, and then deploy it on the target hardware. Now, let us look at what this actually enables in real world. So, TENS model can run real-time on device, even at low resource target. We have been experimenting on very super low configuration and low cost cell phones too. And here are the 3 instances showing where this can really matter. So the first one is defense. At a forward operating base with no cloud access, TENS running locally enables classified document QA, and which is without any cloud connectivity or internet connectivity. The second one can be healthcare in remote field clinics that sit in connectivity dead zone. An on-device mobile model lets anyone to have a real conversation with full medical reference library, like drug protocols, interaction warnings, treatment guidelines, which can be done completely offline. Third one is for industrial use cases. So on factory floors, behind an air gap, operators can interact with entire equipment manuals and troubleshooting guides through natural conversation with no operational data ever leaving the plant or without any internet connectivity too. These are just examples. The same pattern applies to automotive, consumer devices, even wearables, basically any product where cloud AI is not an option. So that's where this can be super utility. Okay, so to wrap up, we have seen how BrainChip enables efficient generative AI on edge and why state space models are better suited than transformers for these scenarios. And today we are opening access to our TENS 1.2 billion parameter model, so you can start experimenting with it and see the potential firsthand. And I would say this is just a beginning. We have more coming on the model and the platform in months ahead. Feel free to scan the QR code to log into our developer website, and feel free to reach out to us using the email and website. Thank you.
Thank you so much. Thanks a lot, Ritik, for the inspiring presentation, and also for keeping it within the 20 minutes. We have a few questions actually from Danilo, from our working group chair. The first one is, you can see also on the screen, what type of bandwidth do you expect to be required from Flash about SSM? Can you provide us some insight?
Yeah, we have been doing some analysis internally, and for that info, I would say, like, you can feel free to reach out to us and we can discuss further on that, more like detailed info on that.
Can you give us some hint?
I think those kind of info usually come under the NDA. So
all right, okay. All right, then let's move to the next question. State space Kolmogorov Arnold networks have been proposed to couple both capabilities, like with SSM and transformer. This helps interpretability while learning univariate functions. Is that an approach interesting for your hardware and software solutions?
That is interesting, and maybe our research team is already looking into that. So thanks for highlighting that. Like we'll definitely discuss about that. But thanks for pointing it out.
All right. Another question, see from Danilo, for Q&A application, like for example, refrigerator maintenance, informal retrieval system like BERT are more lightweight than small language models. What's your opinion on the need to support both?
BERT is definitely lightweight, but as you can see, like when you compare BERT to even ChatGPT 2, which is like a very old model, so the capability which ChatGPT can perform, it's the BERT cannot. So it all comes down to how complex your manual is and how complex your task is, and that's where, like, because you can, what we are enabling is more like you get a small model running on low power on an edge device, and you can do really kind of like complex question answering with a device, which is really interesting. And BERT in some way can enable that, but it all comes down to accuracy of the answers, how much context it's able to understand, where BERT may, and definitely it's available, but BERT may not be the best model for the most complex applications there.
All right. And then one question from Abdel Ali. What is Akida?
Yeah, Akida is the name of our technology. So we are in chip and IP business, and our first generation chip is known as Akida 1500. So it's a product line in our company.
Thank you. Thanks a lot. So we got quite many questions, Ritik. Thanks a lot again for your presentation. I can already see Davis popping up here on the screen. Who's going to be our next speaker from NXP. Hello, Davis. How are you?
Hello, Roberto. Excellent. Thank you. Can you hear me okay?
Yes, we can. We can hear you well. I think you can also start sharing your presentation. Davis is going to give us a talk on domain-specific intelligence meets ARA discrete NPUs. All right, we can also see the screen. I go to the background, and the floor is yours. Thanks, Davis.
Okay. Thank you so much. Thanks for that quick intro. Thank you everyone for being here today. As always, it's a great place to see the latest updates and stay part of this awesome community. So today, as mentioned, we are going to talk about domain-specific intelligence. So meaning for certain applications, certain verticals, certain use cases, domains, and how the R discrete NPUs, which is now part of NXP's NPU portfolio, really meets the needs of today and tomorrow, especially when it comes to edge generative AI, which is what this is all about. Obviously, NXP Semiconductors, on behalf of the team at PLMPU, I'm based in Ottawa, Canada. Really, it's a pleasure to be with you all today. Here's a very quick agenda on what we're about to talk about. So I know you probably don't need an introduction on NXP or Edge AI, but I will talk about AI and NXP and what that looks like today. Then I'm going to talk about the domain-specific generative AI we just kind of referenced in the title around what that really means from a model, use case, solution, software, tooling perspective. Then I'll introduce the R discrete NPU, its capabilities, what it's good for, where it's already used today, and then a call to action invitation to really collaborate and work together on Edge Generative AI. So let's dive in. So it's no surprise that we're seeing this rapid, not just migration of cloud use cases that have been talked about, and I don't need to go into too much detail here. But I think what is surprising, and what's certainly for me exciting, is that we're not waiting for this lag time or impossibility of all the stuff you see here at the edge. It's all happening. It's all possible. New is being made possible, and it's up to us to be creative and solve it. And what this means from an NXP perspective is that we can sense perception, we can think, we can do generative AI, and we can act all at the edge, all on the NXP device or system, I should say. And to be specific, while there's still evolution, training, silicon, semiconductor innovation happening, solution innovation happening on the training workloads, and huge growth there, as we all know, we are really decisive and focused on inference being the bulk of what compute processor needs are when it comes to Edge AI, for certainly when it comes to the markets that you see here referenced. And so this is really building into, again, none of this should be too much surprise to those of us here, but I really want to set up when we talk about, again, today's focus in this very quick presentation, what are the top markets and use cases? It's a classic challenge of horizontal AI being able to deliver good enough results or good enough enablement across a bunch of use cases, or having the ability and the knowledge and the repeatable ability to go deep on each one of these with not just yesterday's AI workloads, but the evolving, constantly changing landscape of what AI success looks like in every one of these items listed here. And so I'm not going to talk about them all today. We don't have time, nor can I. But we are going to focus on some exciting stuff that I thought it was fitting since 2024. We first mentioned that I'd share with you a healthcare and monitoring and diagnostics and medical personal health, personalized medicine specific use case, because on the first one or second one we did in October 2024, I think I showed a very quick conversational HMI, generative AI, Edge AI, LLMs on NXP, and I wanted to revisit that topic, but also show, like what others have shown here today and this week, how much growth has happened. And so that's all the background stuff. Now let's talk about a little more specific around AI on NXP. So I won't be able, again, to get into everything shown here, but it's sufficient to say that on the left-hand side, the processor portfolio has rapidly evolved, and our DMPUs are, of course, today's highlight. The mass market launch just happened 2 weeks ago with our distributors globally, and also we've been in with customers in field trials for over a year now on the flagship R240 product that will be come up a little bit here. This isn't a product pitch, but I do want to say the timing is very relevant. And so on top of the silicon, we have a bunch of software that you might be familiar with, like EIQ. You might see some new stuff here, like it was announced at CES, Agentic AI framework. And so building on this and taking this further and seeing what is really possible from a generic use case, again, that horizontal layer, this is what the full kind of selection or menu looks like of AI on NXP today. And if you kind of immediately go to the upper right-hand side, the more complex stuff, and immediately go to the bottom right corner and see RDMPUs, this is today's focus. This is where we're going to say, okay, let's double click, triple click on what generative AI at the edge. So obviously that's our focus. Inferencing deployments, solution deployments look like with the R-discrete NPU now entering the fray, being a part of the family, and being able to do stuff for our customers that we couldn't do before. Now, it's not starting from scratch. If you look at what our AI story looks like perception, generative, agentic, we're not starting from nowhere and saying, hey, we just bought this DMPU portfolio company. What can we do with it? We've actually always been leading the way, right? And so in 2021, the MCX-N was the first one to have the Neutron NPU. We've always had a portfolio of NPUs as well. So the ARM Vela, Ethos NPU with the Vela stack compiler and stack there. Obviously, there's CPU, MCU, DSP. So again, it really builds on that system level heterogeneous thinking of it's not how many tops or tokens can you run an LLM on, and hey, we did our job. Not at all. And so when we look at where we already are starting from and how this complements what I'm going to show very quickly with the R discrete NPUs is that, we've already done some really exciting stuff. And so I thought it was fitting that last week the PyTorch Europe conference happened. I know there's probably some European colleagues calling in here today. There's the flagship or main event, the main conference event in San Jose coming up in the fall. And so we've been a part of these edge MPU communities. So it's not just the silicon, but also the feedback loops, the ecosystems, the model ecosystems, the CI/CD pipeline, the GitHub upstreaming, all that kind of stuff builds into what a leading success story looks like, at least from our perspective today. Now, again, from software, not starting from scratch, and I want to move relatively quickly. We've done a bunch of work on, okay, what does speech-to-speech pipelines, RAG, I think was talked about earlier, going into multimodal now, so VLMs being a part of the equation. But domain-specific intelligence depends on customization. It depends on controlled customization. And also, in some cases, you want to accelerate the randomness for creative applications. Very quickly, cool product that uses this or can use this is a storytelling device that's private and Edge AI based for children. There they can get, right now it's rules based, so certain buttons correlate to certain stories, audible stories, but they want to use generative AI. It's a perfect match, but they need controls. So think of open-ended domains, the problems that can happen there, but while maintaining and harnessing creativity. So there's both sides, controlling, so user manual type of stuff, medical type of stuff, be very precise in terms of the information you're retrieving, you're chunking, you're indexing. That's part of the game. Then there's also the emerging part of the game for edge devices where you want to accelerate the customization in a controlled way though still. And so how we already do this is with a Python-based, open source-based NXP, maintained RAG database, RAG database generator that creates vector databases for both kind of guardrail stuff, lightweight guardrails, but also customization. What's cool is that you can also, as I think has been talked about before, deploy knowledge bases at the edge that don't need an LM, the overhead of an LM, but can still do customized domain-specific intelligence thanks to embedding models and all that kind of stuff. So I won't do the whole video, but I want to show today, a use case that's become quite common at the very edge. So think glucose monitoring, blood glucose monitoring, personal wearables, very important devices, but devices that you can carry with you anywhere that give you, again, this is one of those cases where you want very reliable information. If you're going to do blood glucose monitoring with LLM or AI and some sensor, you want to be able to ask questions and get answers that you are confident in. That's the domain-specific part. The knowledge base has to be up-to-date, current, and reliable repeatably in the wild, in the field, as they say. And so this is a use case that we've deployed for some time now. That was, again, it's our kind of hello world example for RAG with Gen AI flow. And so if you see on the right, here's your kind of WhatsApp style UI, and you can ask questions. There's wake words. So this is what we've been doing. I don't want to spend too much time here because this is not exactly the focal point of today. But when you take this a little further and say, okay, let's deploy this on all the stuff you see here on the right. So that's on GitHub. Please check it out. I really would love to get this community's feedback and work together. It supports ARM CPUs and Neutron NPU, which is in IONMX. The question becomes, well, what is possible? What is coming? What are we able to do when you start to look at generative at the edge that's already there with R240, which has been there, but not combined in the way that it's been combined before? And so, excitingly, when you look at our portfolio, our EIQ software stack, right now our software is standalone, just to be clear. And if you go check out and look at links on xp.com or any of the portals or web pages right now and say, hey, where's the EIQ R stuff? Truth be told, that hasn't been merged publicly just yet. However, you can imagine the ecosystem with the host processor, that's an obvious one, the power management, connectivity, security, other sensors as well, not just cameras and microphones. This is what the unified stack looks like. And I do believe confidently that it's a new era of Edge AI. We're seeing this already from not just trade shows, but customers and the open claws and GTCs and faster moving than ever, right? Ecosystems of the world, of the AI world in particular. How do we stay connected and relevant and then succeed and dominate when it comes to being an efficient, meaning not just NXP, but the whole Edge AI ecosystem, being able to offer a compelling option to the world for an alternative to just buying more GPUs and building more data centers and using more copper and doing photonics, all kind of stuff. That's basically it. So when you look at what we have available today with the combination, what I just said, what's coming? well, this is coming, this is here. And I think it's really a cloud to edge story where the two work together. And we don't do this alone, right? We can't do this alone. We have to work with partners that are both the big tech players, the independent software vendors, the tool vendors, the sensor vendors, to get the job done for our customers. And so think of a building automation company that wants to go into the future and have a 20, 15 plus years at least, longevity of a product that's going to do AI, but not just today's AI, but AI that's, again, could outlast the whole history of AlexNet, basically, if you look at it that way. So how can we reliably say, hey, this solution you're going to buy is going to work and run the AI software, latest AI software, and not go the way of an AlexNet, basically, if you at the very specific level. No discredit or disrespect to that. So that's an important reference. Now, what I'm saying here is going back to Google, going back to a lot of important players in the space and OpenAI and Hugging Face's platforms, and looking at this combination of R240, Agentic AI, and NXP's existing investments, we've really built an exciting solution that's going to be publicly available. It's in field trials. I encourage you to use the email list here to reach out to me if you'd like to field trial or get on a wait list for. There's other components as well that like our hub and other EIQ stuff that if you reach out on this vein, I'd definitely be willing to talk about other ways to get involved, early access as well, rather involved with early access as well. So the combination, what is coming? Well, this is what's coming. This is what we want to show today. And coming back to the main topic of today's conversation, because I know it's a lot of info, it's always hard to filter, but I want to give enough info while having time for questions. And again, my email's in the slides, and most people here, certainly the organization can get us in touch, and I'll go to the comments. I'm just on one screen now. But all that's to say is what we've built so far, what we have here, what I'm sharing today, is setting the stage and a stepping stone for domain-specific intelligence at the edge. Why do we need domain-specific intelligence? Because that cloud stuff that books travel and answers emails, that's fine, but it's not what we need for our most of 99% plus of our solutions. But we can't throw the baby out with the bathwater, to use, I guess, a good analogy for my next slide, which is using AI for the most extreme situations. And so we've actually thrown the AI into the life and maintenance of the baby, again, not alone, with a partner called GE Healthcare, longtime player in the space, that have worked with us on a new exciting reference design and product that not only is able to do one component like agentic AI or perception AI, but all of them with business logic or really important system understanding, with all the latest and greatest VLMs and LMs, as you see here, in a completely contained system that we built together that is, again, a really good example of what's possible when you combine agentic AI, NXP's existing software and solutions, and R240 and PUD and PUs. And it's not shown here, but it's a subtlety that's important, is one way of scaling up nicely your AI resources and scaling up nicely what you can do with any of these systems here, actually, is you can add more R240s or any future generation to the host system. So think IOMX, think x86, but a host system with depending on activity, depending on how much you need. So we've had companies come to us and say, we know based on our assessment, research, field trials, we need at least a 32 billion parameter model to be of the effective quality and reliance in our, again, longevity, confidence. A lot of it comes to confidence and trust, right? Especially in these domains. We're confident that's the kind of system we need. Well, there's no one product in our portfolio that can run that kind of model at the kind of speeds that they would use or even we would use. However, when you think of the system of a solution, combining multiple solutions, multiple parts, multiple products, we can get the job done. And that's not always the case where you have that kind of clear mark. Sometimes you need to leave room for overhead for upgrading. So we have a lot of long-term partners, very important strategic players in building automation, avionics, defense, aerospace, say, hey, we've worked with you a long time. We've been in AI for a little bit now. We don't know exactly what, but we know we're going to need more compute, more horsepower in the future. And so having a more quantitative and informed way of not only being able to say, hey, here's our pathway, but here's quantitatively the pathway, is what R240 offers at a system level to plug and play, upgrade your compute. More modules on this host that can maintain it, depending on bandwidth and performance, is your pathway to bigger, better, latest models, or more models running in parallel. Some of the stuff is parallelizable. A lot of the stuff I see nowadays, honestly, is more sequential, where you need a visual outputs and then a retrieval or some kind of embedding to be, input as input to an LLM. And then that output goes somewhere else, and it's not really parallelizable directly, but it is executable heterogeneously, which is what is amenable to a system like what I'm showing here. And so to give you a very recent update, very exciting update, we're working on Agentic AI at the medical edge, building on the kind of individual like medical image or diagnostic machines we've shown before, which is already successful in building. We've gone a step further and said, well, with Kanara, with R2, R240, R2 is the technology, R240 is the product, and with other stuff. Well, now we're really starting to, I like to say, live in the future when it comes to what we're doing with Edge AI and Agentic AI. And so I think this is a great pause point to kind of take a snapshot of this isn't the only thing we're doing, but it's certainly a good example of domain-specific generative AI for a domain that needs high quality, needs safety, needs innovation, needs creativity, needs partnerships, and needs AI. So, this is where I think I'll pause today in terms of specific demos and stuff. I will have a quick summary slide. I'll try to, I think I have my email again. If you'd like to field trial the Agentic AI framework, that's software. You can find all the hardware and modules and stuff on xp.com. Again, I'm not here to pitch or share that kind of stuff, but I really love these kind of the forums to share as a community what we're working on that is not just helpful to us and our customers, but helpful to communicate what we can do together. And so that said, that's it for today. So here's what we do: remote patient monitoring, integration of multiple biosignals, smart interaction with wearables, home devices, healthcare. So think of like remote medicine or telemedicine, or a lot of point of care is moving away from centralized locations like hospitals as available to other residential or in-home or other locations where, again, with the right guidance, with the right systems and AI, we can do so without having a drop in quality or efficiency. That's the name of the game with this kind of stuff. And so with that said, the key takeaways, I hope that come clear, and I hope that you remember from today, and we'd love to talk with further on our, we are not the only player in Edge AI, obviously. We are becoming, I think, increasingly not just from ourselves and our own stuff and own claims, but partners like Meta and Google and others, that we are a recognized leader. We have more scalable software than ever. We have Gen AI Flow today to run Gen AI at the edge. We have a Agentic AI framework that you can reach out to get early access to start to play around with. I'd love to invite you to, again, work with us, work with myself, work with the right teams on domain specifics that I showed at the start of this presentation that all of us work in different ways anyways. So again, I don't think that's the hard part. I think what's the hard part is obviously always, being able to focus and being able to execute, not just at the research lab level, which is hard in itself, but also at the real world level. So, always eager to learn more. Thank you very much for the host, for the opportunity to be here. Let's work together to make AI safe, secure, and sustainable today. If you want to know more, this is the one-stop shop for NXP AI stuff. I forgot the link, sorry, for the page for R240, but there's a lot of stuff out there today. And again, this isn't a product pitch. I just want to share what's new. There's my email. So anyone on this call, anyone who watches later, please reach out. Anything you saw here that's interesting or relevant, I'm more than happy to engage with you on. And with that, thank you so much, everyone. I'm going to stop sharing now and hope there's some questions.
Thank you so much. Thanks a lot, Davis. A lot of insights from your presentation. I was also reflecting on the fact that during the last Gen AI Forum in November, I was also presenting some sort of a recap about what has happened during the previous Generative AI Forums. And I was highlighting that one perhaps piece missing was that so far we hadn't seen much work related to RAG at the edge, for example. And I can notice actually that already starting from the yesterday presentation and today during the first two presentations, we start to feel that gap in this respect. So I think this was a very important piece somehow missing or not much developed.
No, that's great. Good memory.
Yeah.
Yeah, no, sorry. Good feedback. I think I need to get more people other than myself to present here, but sometimes it's great to get more people involved. But good memory. In November, we did share, and you're absolutely right. Even though the context sizes for the latest models are like 1 million tokens and it's growing, RAG is at the edge, especially for real time, for reliable, frozen in time, but updatable, not one-off retrieval. It's a necessary part of the pipeline. There's also an argument for just load the context window, but that's not our game. And especially when you talk about compute, not always the best way.
Yeah. Thanks, David. So we have a few questions from the audience. I'll try to pick up a few. For example, from Thomas, is there a limit when connecting multiple ARA24 OS? Are there any bottlenecks in such a scenario?
Great question. I'll answer quickly because it depends as usual. However, R240 itself can connect over M.2 module, M.2 key. So there's a module for that. There's a PCIe, and then there's a USB module. So the limit depends on the host bandwidth and the host lanes connectivity, how much basically can the host add. We see configurations usually for NXP on IDMX 8 or 9, for example, of 2, so 2 on the Freedom Pro, 2 on the M95, which has 2 lanes, 2 modules, for the R240s. However, your performance is going to depend on the host system more than the R240, and all that stuff is online. There it shares, some guide or suggestions on if you want to run this, here's the required bandwidth and memory, all that kind of stuff. But really good question, and I think that's, if you look at the next 12 months, that's the direction that needs more exploration.
Then there was a question also from Danilo. He was asking an opinion on whether you see, like in terms of pervasiveness of application, more audio conversational or medical oriented application. What's your take on this?
So another good question. I'll try to be quick or concise rather. The audio conversation models, especially in multilingual and for real world, like under noise and stuff, reverb is becoming incredible. So at Voxtral, Mistral, so domain specific, and it's becoming cost effective. Like the latest Google Flash API is very, very high quality, but also relatively affordable for constant streaming, audio bulb, etc. So that's doing great. However, if I understand your question correctly, I'm medical oriented. That is also, I don't want to use the word catching up because it's not exactly true, but that is gaining more momentum. Someone mentioned state space models earlier. I think Liquid AI is presented here before and others. So there's a need for, and also physics inspired or, world models basically that maybe are medical oriented. That's really not a whole nother topic, honestly. However, the audio conversation stuff is really working well today. It needs work to be done to make it optimized for the edge, let's say. However, both are gaining steam. Pervasive, well, I think it's really depends on the use case, but audio is pervasive for sure and becoming more so, not stopping.
Yeah, you also just mentioned word models. I expect that in the next forums we will see more and more
I agree.
input from
word
model at the edge. One more question from the audience, very quickly. Question on what are the target boards here? I guess in terms of computing capabilities, are we talking about MCU and or MPU type of devices?
So we're talking about MPU, although there's MCUs involved in, say, an agentic system for motor control or for sensors. So that's not part of it. However, target boards, there's 2 that I'd say are the most target, but we can also support x86 systems. So ARM-based host processors that are built on Yocto, so Linux, that are NXP, but not limited to XP. However, the ones that I'd say are for the R240 are the Freedom 8M Plus. So that's 4 ARM Cortex-A cores, a GPU, DSP, Connect 1 240, the Freedom 9.5, which is just announced that last week, which is 6 Cortex-A cores, the Neutron MPU. So that agentic MedGemma system I showed, the target board is the 9.5 with the R240. It was by way of a colleague in Germany that contributed that. So that's the board they're using.
Thanks. I have actually last question from my side. Davis, you were moderating the first Generative AI Forum, right? And it
Correct.
happened, as I mentioned earlier, 2 years ago. A lot of things have happened in between, completely revolutionary things if we think about from where we started and where we were standing a couple of years ago. What are your expectations with respect to what is going to happen in the next couple of years? Your personal perspective, where do you see both research and development? Where will be the traction in terms of R&D?
Sure. It's always a good question. I'll do my best to be accurate, but also, share in the time we have, because this is always a topic that I think is embedded somehow in these conversations. And hopefully, I'm not being lazy, but I think it's the right answer. Song Han said on the first one to a similar question, the future is scaling up, scaling down. And I think that's still true today. It's still true going forward, where we're seeing better performance scaling down with better quality, but also the constant scaling up. And you can see it in the latest releases of like the Light RT version of the Apache license model for the Gemma 2B and 4B. Small models have scaled down, but are super good. And then you still see the latest and greatest scaling the other way, scaling more devices. Look at the scale of OpenClaw as an agentic system, fastest growing dev project ever. So I think scale is becoming a really powerful concept. And again, so I'm answering the question with someone else's answer, but I think it's if anyone to borrow from, he certainly knows his stuff. So good question. Thank you.
Thanks a lot. Thank you so much again, Davis, for the presentation and for the discussion. So we can.
My pleasure.
Thanks a lot again.
Have a great day.
Bye. Thank you. Bye. We can then move to the next presenter, Blake. Hello. Who is presenting?
Hi, can you hear me okay?
Yes, we can hear you. So Blake is from Godel Space and is going to give us a presentation titled "From Orbit to Action: Running NASA Foundation Models on Edge Hardware for Real-Time Disaster Detection." This sounds very exciting. Looking forward to hear more. The floor is yours. Thanks. You can start sharing your presentation.
Thank you. Let's do that. Please let me know that you can see my screen.
Yes. Yes, now we can.
Excellent.
Thank you. Please go ahead.
Oh, okay, great. Yep, so my name is Blake Bejarano, and I am giving a presentation on behalf of Vikash Kodati for Godel Space. One thing that I wanted to quickly mention is I'm actually here at the International Conference on Learning Representations in Rio de Janeiro, so very happy to bring some of the sunshine from here into our meeting. Today, I'm going to be talking about Godel Space's recent development and application for orbit to action for real-time disaster detection by running a 300 million parameter vision transformer model on a Jetson Nano from NVIDIA. So let me go ahead and get started. And I did want to just go ahead and say, I apologize for Vikash not being able to attend today. He certainly wanted to be here. So first things first, we'll go ahead and tackle the big question of, why this problem. First off, this again is not a technical, or it's not a product pitch. It's certainly a technical deep dive into what happens when you take this 300 million parameter foundation model and you force it into 8 gigs at 15 watts. So that is the optimization essentially that we're interested in today. But the problem of why space needs edge AI is literally exactly that. The constraint matrix in space is uniquely unforgiving. You can't increase bandwidth mid-mission, and you cannot swap hardware. You can't SSH to debug, and your thermal envelope is hard limited by the vacuum. So it's an extreme environment, to say the very least. And the reason why we need edge, specifically on satellites, for being able to do real-time detection for anomalies for disasters, is that ground processing actually adds hours to the amount of processing time, and that latency leads to critical infrastructure being destroyed, and ultimately a slower response time to be able to better enable us to mitigate any of the potential aspects of a disaster happening to a local environment. So that's one thing that I'd want to mention in that sense. So obviously satellites generate tons of data, terabytes daily, but they only downlink a very small portion of that. And the latency in ground processing is actually fairly substantial. It adds an additional 4 to 24 hours of latency. And then the other thing that I want to say is in terms of the parameters of a satellite, power is the most precious resource that you have. Both the model that's running, the 15 watts, is also being used to stabilize the environment and make sure that all of the critical systems for the satellite are operating the way that they should. So one other thing that I could quickly showcase here is just a couple figures from the some recent disasters that had happened, like the Palisades fire in Southern California, cost an estimated $50 billion. And that is just a really quick synopsis from FEMA. And similarly, the Marshall fire in 2021 cost an estimated $2 billion in damage. So there is real financial value in being able to provide a lower disaster response time. So that is just kind of setting us up for the problem. And let me go ahead and just mention, I wanted to be able to run a couple things in the terminal for you guys today, but due to time constraints, I'd be very happy to connect afterwards, and I'll just show some of the basic reporting around the optimization schemes and some of the benchmarks that we have there. But this is essentially the pipeline, and let me dig into the hardware a little bit here. Okay, so one thing that I would want to make sure that I mention is that Prithvi is a vision transformer model, and it's pre-trained on harmonized Landsat Sentinel-2 data. So it's 6 spectral bands across the 4 temporal steps, and it's actually that temporal dimension that makes this both powerful for real-time anomaly detection, but also means that the input tensor is significantly larger than a typical RGB model. So essentially, the tokenizer, it's going to create a spectral band-aware tokens. So the attention patterns are fundamentally different from NLP transformers. And the other thing that I'd want to mention here, specifically related to the hardware, is that the Edge hardware itself is an NVIDIA Jetson Orin Nano Super with 8 gigs of unified memory. And that actually becomes quite challenging to deal with. And I'm going to spend the bulk majority of today talking about the optimization and the problems that were overcome to be able to utilize this hardware, and then also talk about some of the future paths for way forward to being able to actually deploy this. And yeah, that is a really quick synopsis on the hardware itself. Oops, I didn't even click on that. And okay, so what is it that we're really doing here? So the first thing that I'd want to mention is that we're using pipe-ripped export. Being able to export to Onyx, the temporal spectral structure that I had mentioned before creates specific blockers that were needed to be solved. And on the hardware side, the Orin Nano Super gives us 67 tops into 8 at 25 watts, but our operational sweet spot in terms of power efficiency turns out to be that 15 watts that I had mentioned. And I'm going to show you the power profiling card to hopefully make that a bit more clear. So that is what I wanted to say in that context, but this is essentially the pipeline that we're looking at. So PyTorch export to Onyx, OPSET 17, and then the Tensor RT FP16. And then the deployed engine, which we were able to reduce substantially in size. So let me go ahead and head over to the next slide. So one thing that I would want to maybe mention here, specifically with the exports. So the Onyx export, we used tracing rather than scripting because Prithvi's attention implementation uses dynamic shapes PyTorch cannot handle. So OPSET 17 was required for a scaled dot product attention operator, and we added dynamic axes for batch, but kept the spatial dimensions fixed at 224 by 224. The other thing that I'd want to say is that at the second stage, the Tensor RT build has 8 distinct engineering blockers that we had to handle. So that is one thing that I'd mention in that context. And the largest of those was actually NVMap, which is Jetson's native memory allocator. So this imposed some contiguous allocation limits, and the CUDA malloc allocator bypass routes through the standard CUDA malloc instead, fragmenting the allocations into manageable units. So realistically, what we want you to get out of that is just that this single change reduced the allocation overhead by roughly 15%, which is fantastic. In the stage 3, would be that 619.9 megabytes engine down from 1219 megabytes Onyx. So that is roughly a 49% size reduction, moving from FP32 weights to FP16 at very little cost in terms of performance. So that is one thing that I would want to mention there as well. So you can see in terms of FP16 versus FP32 baseline, we actually had to do a 2-phase validation because it's just was impossible to have these CPU ground truth as well as the GPU Tensor RT inference running at the same time on the Jetson Nano. So these were ran separately in order to reduce any possibility of cross-contamination as well. The other thing that I'd want to mention here as well is that the FP16 rounding across 24 transformer blocks remains within acceptable bounds, and you can see that the mean absolute error is certainly within the specified threshold, and then also the cosine similarity is within its threshold as well. So I will go ahead and just quickly mention that. And so these are some of the actual results. So one of the things that I would want to make sure that I mention here in this context is that these are not simulated numbers. 400 tiles through the actual engine at each of the NVP models power settings on the physical or in nano super hardware. And then the Pareto curve is the key insight. So I'm going to show the power profiling card here in just 1 second. But one other thing that I could mention in this specific context is that going from 15 watts to 25 watts gives you roughly 50% more throughput, but costs about 30% more energy per tile. So at 15 watts, you actually end up getting 9.7 tiles per second at 1.29 joules per tile. And at 25 watts, you get 14.4 tiles per second, but at 1.7 joules per tile. And when, again, energy is the most constrained resource that you have, this optimization is actually very key for being able to provide value in this specific setting. For orbital deployment, where, again, that the power is the binding constraint, the full 400 tile scene completes in 28 seconds at the 25 watts, and that's well within any orbital pass window. So the thermal peak also with sustained usage across all 400 tiles is 62 degrees Celsius with 0 throttling. So that is super important where in a satellite when you cannot add a fan to be able to cool things off. So I wanted to make sure that I mentioned some of the thermal capacity in that case too. I'm going to quickly screen share my benchmarks. So let me do that. I'm going to stop sharing very quickly. Okay, and let me screen share again. So here we go. So this is the power profiling card, and you can see that there is a latency of 68 milliseconds and the 1.29 joules per tile that I had mentioned before, with the maximum sustained thermal being 62 degrees Celsius. And you can see that the accuracy is also as intended there. Let me go ahead and showcase this really quick. In fact, let me move this over. So you should still be able to see that. Please let me know if that's not the case. So just a couple things about this. So one thing that I wanted to make sure that I mentioned is the following. So we exporting a vision transformer model to Onyx is certainly not trivial, and Prithvi uses custom position embeddings. So multi-head attention with spectral band aware tokens and dynamic input shapes. And again, we used offset 17 with tracing, not scripting, because this model has data dependent control flow and it's spectral encoding. So dynamic axes for batch and spatial dimensions, essentially. And the Onyx model is the interchange format, portable to any runtime, but the real optimization is actually happening with TensorRT. So one of the things that I could quickly mention here as well in that specific context is the following. So let me go ahead and scroll down a little bit over here. So you can see the sustained throughput. So for a battery saver mode where maybe you need to run some background tasks at 7 watts, you can see that the throughput is 3.6 tiles per second. 15 watts really is the optimal output. So that's 9.7 tiles per second. 25 is 14.4. And then this is max N. So this was the highest level that we tested. One of the other things that I'd want to mention here too is the Pareto curve. So you can see that is essentially listed here. And then one of the other things that I would want to make sure that I mention is, again, the thermal behavior, since cooling is certainly an aspect that needs to be addressed when it comes to satellites and imagery. I'm going to hop back over to my slides now. Let me share again. And so one thing that I would want to make sure that I point out here, that the int 8 was actually a complete dead end. It would have provided a 2 times speed up, but 23 out of the 24 transformer blocks actually requires 578 megabytes of contiguous memory. So while that memory was available, it wasn't contiguous. So there's just a physical ceiling on the 8 gigs of unified memory. And we tried 4 different approaches. All of the approaches failed identically. The path forward would be to do int 8 on an AGX Burn 64 gig on flight hardware, or potentially doing some cloud calibration cache. But what we would like to do is target 10 to 15 milliseconds per tile with this updated hardware. And there are some plans for later this year that I'll talk about in that specific context. But one of the primary focuses of this development was the semantic compression. So this is a fantastic bandwidth solution. So the foundation model embeddings compress the scenes. So again, each tile, the 400 tiles will make up a scene. So it is able to compress these scenes, the satellite imagery scenes, from hundreds of megabytes to kilobytes. And then the downlink and embedding detection results is not oriented around raw pixels. So edge computing actually becomes fundamental to satellite bandwidth constraints. So that is really the takeaway from this. That and int 8 just absolutely would not work on the 8 gigs of unified memory on the Jetson or in Nano. So that is one thing that I could mention there. And what I would like to do, since I realize that we're constrained in terms of time, is I would like to be able to show a very quick demo. So let me go ahead and do that. And I'm going to share this tab instead. So you can see here is a demo. Specifically, the one thing that I would want to make sure that I mention here is that everything before this is just theory and some benchmarks, regarding latency and the tiles per second, et cetera, and the capacity in terms of power. But what you can actually see here is that this is an actual HLS burn scar imagery. So this is from the Palisades wildfire outside of Los Angeles. So in fact, I probably scroll around a little bit in that context. You can see here is the areas that were affected by the fire, and this is the most substantial section, but then you also have this area over by Lawrence Livermore too. But let me go ahead and pop into this. So one of the things that I wanted to make sure that I mention here is that this is a real 512 by 512 geo TIFF that goes through the full pipeline, tiling, TensorRT, FP16 inference, reassembly, and an overlay on a SysTM.js globe. So this container is about 5 gigs down from 12.8 through base image optimization and dependency pruning. And specifically regarding the latency, it's about 103 milliseconds median per tile at 15 watts. So that number comes from the 400 tile runs across 4 power modes, not just some cherry-picked best case. And then the SysTM.js visualization is not just for show, it actually demonstrates how a ground station integration pattern. So edge results arrive as a lightweight JSON with confidence scores, and then the globe renders them in this context with terrain and imagery base maps. So you can actually see, if I scrolled in a little bit, where some of the critical infrastructure and facilities are. So I'll even maybe go in a bit further than that. Some of the buildings, you can see the highlighted sections here that are showing up. So see buildings, roads, and then you have this real-time anomaly detection that can help you better protect those specific facilities or buildings, etc. The other thing that I'd want to show here too is the response pipeline, or I'm sorry, the timeline. So you can see that the amount of time in order to have the real-time detection from the edge is much faster. In fact, you can see there's a 17.2 hour advantage over sending everything down to the ground and then having it processed on the cloud and then doing the response, as opposed to doing the processing from the satellite directly, downlinking the results, and then being able to actuate on those results, specifically with probably some agent oriented advice on how to address those specific concerns. So that's one thing that I'd want to mention there. The other thing that I would want to show too is this pipeline. So you can see here is this little pipeline running. So it's requesting the task, the imagery is acquired, it processed on the edge, and then the intelligence is published. So that is essentially how that works. You can see the downlink bandwidth. So there is quite a bit of bandwidth saved through our specific application and optimization techniques in that capacity. I'm going to head back over to my slides. And one of the things that I would want to go ahead and mention here as well is what comes next. So later on this year, we should be sending our hardware actually out on its first orbital deployment with a partner satellite with a 4-band camera. So that's RGB plus the near infrared. So that is one thing that I would mention, and we're really excited about that. And then in terms of flight hardware, the Jetson AGX Orin 64 gigs with NT8 targeting 10 to 15 milliseconds per tile. And our overall vision is that every Earth observation satellite becomes an intelligent, autonomous observer. The one thing that I would want to go ahead and quickly mention in this context is if you have specific technical questions about the implementation or optimization algorithms for the containers, the pipeline, etc., Vikash is definitely the head honcho of Godel Space. So feel free to contact him at any time with any additional questions that you might have in that context that I'm unable to. And then lastly, I would just want to talk about the edge hardware profiling. So again, this was on the Prithvi EO 2.0 300 million parameter model with NVIDIA Jetson Orin Nano on 8 gigs of unified memory. Here are some of the specific stats for you. So 68 milliseconds for P50 latency at 25 watts. So that's optimal speed. 1.29 joules per tile at 15 watts. So that's the optimal efficiency that I'd mentioned before. And then substantial cosine similarity between FP16 versus FP32. So you get some really good gains with low loss in that context. And then the max thermal capacity is 62 degrees Celsius under sustained 400 tile workload. So the 4 power modes that were tested were 7 watts, 15 watts, 25 watts, and then max. And again, if you have any questions, you can feel free to send a message to Vikash. And then if you're interested in the full report, you can just go to demo.godelspace/report, and you can look at the report, the profiling card that I'd shown earlier. Thank you so much for the opportunity to give a talk and to interact with your community. I'm really excited to be here. And yeah, I will take some questions or pass them off to Vikash later and connect you.
Thank you so much. Thanks a lot, Vlad. I think this presentation is very appreciated, especially it's coming a few weeks after Artemis 2 story. So it's very nice to see this first presentation about generative AI in a kind of space context at the edge. So it's very exciting. I think we have a time perhaps for a couple of questions. There is excitement about this talk. I can perhaps take one. It was actually also coming from our working group co-chair, Danilo, which is also discussing about that possible issue that this kind of hardware environment could face because of the radiation, and if the company is also, perhaps if you can provide us some insight on whether the company is also working in this respect, and what are the possible trade-off and limitation in this case, if you can give us some insight, if any.
Yeah, that's really interesting. Yeah, so one thing that I can say is that there are specific hardware modifications that can be made to harden the hardware against the effects of radiation. So that is certainly a concern in that context. We're definitely more on the software side and use the hardware that we're able to procure and do testing with. But from my understanding, there are specific modifications that NVIDIA is releasing. I was actually just at the GTC conference about a month ago. So there are certainly people that are talking about this as a potential challenge. And I think that that's definitely on the radar of the folks that are trying to deploy these things operationally.
Thanks. And another question, maybe again from Danilo, and then I will also ask a question. This one is about multimodality. What type of sensor do you device feeding the small language models? What kind of interactions?
Yeah, so in terms of the actual sensors, like I mentioned earlier, it's a 6 spectral band with 4 temporal steps. So that's essentially the sensory equipment that is being used in this capacity. And the reason why it's being used is it provides additional nuances for real-time anomaly detection, specifically just in terms of Earth observation and what is, I would say, fairly standard for the NASA Foundation models. I apologize if I'm not able to answer that in a more formal capacity, but I'd be very happy to forward your question to Vikash in that context too. So.
Thanks, thank you. And I have just a curiosity. You show us a lot of interesting insights, and most of the tests that you have been running, you mentioned about the use of the Jetson Ori Nano, right, as a single board computer for experimentation. Are you perhaps considering to target even more resource constrained devices, or devices that do not necessarily embed the GPU, but they might also use some alternative type of AI acceleration? Is it something in your roadmap at the moment, or not yet?
I think right now the plan is to somewhat step in the opposite direction, to use the AGX, the AGX 64 gig. So we'll actually have 8 times the amount of memory.
Indeed.
So.
Yeah, so the less constraint. Yeah, so
exactly. Yep.
Is it because you face some specific bottleneck that with the Jetson Ori Nano, or you just want to push further the performance?
There were definitely multiple bottlenecks that were addressed throughout the process, and realistically, I think that being able to flip the bottleneck in terms of having the image acquisition being the bottleneck as opposed to the downlinking would be extremely important for the specific use case. So,
all right, yeah, we look forward to see what comes next. Thank you so much again, Brad. Thanks a lot for your presentation. Very, very inspiring, and we look forward to hear more about what you guys are doing. And I think we can then move to the next presenter. We have Tara from Murche AI by AGI Innovation. Hello, Tara.
Hi, Roberto. It's going to be Majid who's going to present.
Okay, all right. Okay, then let me also add Majid into the. Thank you so much, guys. For I will leave then Majid on stage, and
yes.
Thanks. So Majid, can you start? Yes.
Yeah.
Thank you so much. So you're going to give us a talk on total recall at the edge, a deterministic universal memory layer for agentic AI. Thanks a lot. We look forward to your talk. The floor is yours. Thank you.
Thank you very much. Glad to be here and presenting at Edge AI Gen AI Forum. My name is Majid Fikri. I'm CTO co-founder of Edge AI Innovations, along with Tara, who is the CEO and co-founder. And we have 2 products in our portfolio. It's Murche AI and Memento AI, which we'll talk about. We specialize on retrieval and memory layer. And during the next 15 to 20 minutes, I will talk about the importance of memory layer for agentic AI and Gen AI. So there was very interesting presentations before us, both Ritik and Davis. They mentioned RAG under system and deploying it on edge along with different intelligence models or agents. There has been a lot of progress recently on these 3 items, like perceiving images, text, and actions on the sensors side, pairing it with language models, VLM models, and advanced reasoning models. And then we expect now the LLMs or intelligence system to act, to use the tools, to do things, to make decisions. And maybe it will be a robotic coming soon, the wave of robots that will be acting in physical AI. But one thing that is not mentioned a lot yet, which will become more and more important, is the memory. And I would argue that memory is not just RAG, it's a lot more to it. And it's a real big bottleneck right now, which will become more and more important going forward. Right now, the biggest challenge is that memory would also be hungry for resources on the limited resources edge. It's a very critical data. It deals with real important information that you don't want to leak. So there's the issue of also latency. There's the issue of security. You don't want data to leave. And also memory itself is not just the retrieval, it's not just RAG. It has a temporal context. It would be conflicting memory in it. So it requires intelligence on its own to keep the memory. And if we deploy it properly, it would give another superpower to the agents, and not only domain specific knowledge. So far we have, like Davis also talked about, domain specific knowledge. You want your robots or edge intelligence agents to be specialized in what they do. And what is the best way of creating this specialization? By keeping the memory and a long running memory. So like the same way that a human, let's say, works in a specific domain, over time, what it learns through the real interaction and its own unique memory gains some individuation and becomes like very fit to what they do. Now, and here in this slide, I'm kind of preaching to the choir because everyone here is really into building on edge intelligence. But I just wanted to emphasize what's going to happen. There's going to be a collision of rules and regulations. In the US, we had the Cloud Act. Basically, US government can compel any US-based cloud provider to give them access to the information of the customers. And on the other side, on EU, GDPR Article 48 says that whenever you put the transfer data to other jurisdictions, you need to think of protections. You cannot just deploy things on cloud. And these two are going to collide at some point. And this is a legal collision because now we cannot just say on the cloud, I'm putting my deploying on a server in Frankfurt, and therefore I'm still in Europe because that physical location now is irrelevant. If the government gets involved, practically it's not protected. Now, so especially for health tech, fintech, defense, government, and industrial IoT, there would be additional push to do things on the edge, definitely. Now, going back to the problem of retrieval. So everyone knows that you have this powerful tool which we call semantic search, which you don't just search keywords anymore. Now we search through embedded information, which gives us what the meaning. It leads us to the meaning of the text and context, and that's also refines the context for LLM. And the better we do it, we save resources, and we also make our LLM work more accurately and more grounded on the truth and facts that we want to feed it with. Now, the state of art, like everyone is using, is HNSW, which is hierarchical world navigation system, which was introduced in 2016. It's a very fast algorithm, and almost all of the vector databases are based on some version of this algorithm, which is very fast. It's turns an order of n search into log n, which is fantastic whenever you can do that. But it has some shortcomings, which are especially becoming more painful on the edge devices. So on the graph, I want to just explain, if you're dealing with 1 million vectors, let's say, and these are even small vectors of 300, 400 dimension. Usually we deal with vectors of 1,000 dimension, and that's 1,000 float numbers. If you just look at the float numbers, like you would need 1.5 gigabyte of memory just to keep your vectors. And then on top of that, you need to keep the HNSW graph in RAM. And if some part of this graph is missing, you would have a severe degradation to your search quality right away. And there are also quantization methods or compression methods, like a scalar quantization. Now on Murche, we have also came up with our proprietary method of compression. We call it MIB, which stands for maximally informed binarization, and I'll explain what it means. But on the problems that we're trying to solve is that heavy dependence on RAM is problematic. HNSW is not good for storage-based recall, and it's also at the end it's an approximate method, and whenever at any stage you have problems, you wouldn't get the accurate search results. And for its best operation, you need GPU enhancement, and then GPU is also prime real estate on the edge. There's a slow indexing and slow re-indexing because you have to maintain the tree structure, navigation structure. So it's not suitable for fast transactional memory that we need for agents. And it's difficult to rebalance. Basically, as soon as you have 10% change, you have to rebalance it. And it's designed for static data set. It's not really designed for very dynamic systems. And also when you move from one device to another device and the specs change, the RAM computation changes, you will have to rebalance and tune it because it's very sensitive to the tuning parameters. And retrieval at the edge is now very scattered. There's so many different solutions existing. Even this is not up to date. And what I see the trend is everyone who's putting like LLM, Gen AI on edge, they try their own version of building some kind of RAG tool that fits to it. And the commercialized versions out there is not that appealing. They're not solving all the problems. They're not deterministic, which gives grounding to the system. They're not most of them are not CPU native, and they also need a lot of RAM-based systems because at the end of the day, most of them still rely on HNSW for performance. Now, this list is not exhaustive and it's not new, but it's just giving you the overall state of if you will go shopping for retrieval on the edge, what you have. Now, to the problem of compression, there is millions of ways you can do compression. There's no limit on how you can do compression in many, many, many different ways. 32x compression is kind of like the most extreme way. So you go from float, every float point would be represented by a single binary digit. That's like a 32 compression means. And you lose a lot of information and you lose a lot of capable like accuracy with that. And usually it very extreme quantization still achieves like 88 to 93% recall accuracy with binary vectors. But what if we could maximize the recall. So same compression, some of our benchmarks are published already. It's 100% recall using information theoretic binarization, which is on the foundation of everything that IT is based on. Is Shannon's theory of information. You have a limited channel, you have a random signal. We treat it as signal processing technology. So, and then we know how much we're losing. And then on the other side, on the retrieval side, we use information theory to regain the loss of information, and that's called information theoretic score. Yeah, so I explained this. So we go from float to binary and then recover it. It's a patent pending method. So basically, instead of compressing the geometry in the tree structure, we just push it into like entropy, maximal entropy binaries, right? And the good thing is that now, if you can rely on a very universal way of compression, no matter what kind of embedding you have or dimension you have, you can still rely on the same kind of compression. The good thing is that you can change the architecture, and you can leverage the CPU architecture very efficiently here, because the RAM, where HNSW has to leave, is on the DRAM, and it would be using gigabytes of your DRAM. But once you turn vectors into very, very tiny bite-sized indexes, basically, these can leave an L3 cache on the CPU, which then you can also, along with it, the second stack that comes after the compression, we'll call it EDM, efficient distance metric, which is basically a Hamming distance calculation. And we leverage the pop count. Pop count was introduced by Intel in 2008, and now it's supported with all the architectures, even ARM architectures. Basically, natively, you do a very fast operation, one tick of the CPU clock. You can run a ton of these distance metrics, which is a lot faster than cosine similarity and compared to zero float point. And then you get a big kind of candidates. Now you need to narrow down the candidates using the information theoretic score. This information theoretic score comes from my PhD studies. My background is in atmospheric science, so I was working on validation of forecast, rain and snow. So this is normalized, which is very beneficial. It's this normalization applies with relevance thresholds that you can rely on for actually grounding your context even more. You can put thresholds. Anything below that threshold means it's irrelevant to my context, to my query, and automatically cleans up your context, and it's mathematically grounded, and it's not relying on LLMs to do the cleaning. So that's another advantage. So we have deployed it on Murche. Trademark is a cloud architecture where we offer this as the entire architecture that deploys natively on cloud, on GCP and AWS, and it brings in the 400 different assets that take care of everything from ingestion, from embedding to storing. It pairs with high throughput databases, and then just decentralizes the compute and the retrieval. And it worked very well on cloud because it saves a lot of cloud resources, and it's highly scalable. And then we also work on the VPC deployment on private cloud. And now we are actively working on the edge node, which we are very excited about. There's still a lot of engineering that goes into embedded devices and optimization for hardwares on that. but we want it to be CPU native. And my argument is that every modern CPU should be enough to handle the files at a large scale, handle the context at large scales. Now, the next point I want to make is that RAG is not memory yet. RAG is just the beginning for us. So you have the LLM inference on the top, and you have the prompt and context window, and you have the vector stores. But agentic memory requires a lot more. So we have identified 6 design principles that any good AI memory should provide to the LLM or to the agent that's running. You need to have a good temporal versioning for the agent to know what happened when and what is the sequence of events that happened. You need to have a conflict resolution if there's something happening now that's conflicting with what was told before. You don't want to accumulate conflicts in a memory. There should be session isolations, zero latency writes and also read, which HNSWs cannot do a high frequency writes as fast as the agents would need it. It's kind of log of all the activities. You need to have a thorough writing system. And then deterministic recall. You don't want approximation, because what you want might be a needle in the haystack, and you have to find that needle. And it has to be on-prem compatible. Now, what we have built, this is our new product, and we're very happy. It will be officially launched by end of this month, April 30. We'll be at San Francisco at Capgemini when releasing this. So Memento is a Python-based local agent for memories. So it becomes an agent itself and helps the current agent. It exposes 3 fast API endpoints: remember, recall, and answer. And it also provides a CLI conversation channel with the agents. Again, the main thing is remember, recall, and answer. And remember means how tells or and educates agents on how to save their memory and workflow, how to commit what they understand is happening, the perception of the events into the memory. And recall brings it back with the Murche search algorithm, tells it back what's happening. And answer is actually the full RAG. Okay, so answer is recall plus some agentic information. So that's where the RAG is wrapped inside. It's only one part of memory is the full RAG system. Yeah, we compare that with existing benchmarks. One of them is long mem eval and Locomo. We're not burning tokens in the ingestion. It's just a very, very highly efficient RAG system underneath that achieves very high numbers on accuracy. So I think I still have a few minutes, and I probably want to show you some sneak peek on how Memento would look like. So it's we call it the memory that AI agents love, because those 6 principles that I talked about comes from having extensive discussion with the agents themselves. So pip install Memento, and you get the install right away, and you can you can connect it with your existing agent. You create memory agents that pair up with the existing agents and expose it to remember, recall, and answer. The architecture is reliant on the very efficient Murche memory system on the back end. So memory engine goes back and then streams back into the agent whenever the context is needed. Yeah, I talked about the 6 principles, and among the existing agents, we're the only one that are currently covering these angles on agentic memory. It also gives you a local dashboard. So you just say Memento UI, Memento dashboard, and it brings you the dashboard, which gives you full visibility into everything that's happening as this is running on your local. You can explore all the logs of all the memory. And as I said, it has a conflict resolution. So it goes back into memory, searches for conflicts and reports you, and you can resolve it by making some easy choice options. And it also gives you full analytics of what's happening. Now, it natively pairs with a lot of agentic workflows already. You just say Memento connect with the agent you're using. It also connects with pairs with local agents. And we will be presenting this with Crew AI and Llama Index next week. So they're the orchestration platforms for a lot of agents. One thing on the side, we also made the surgical version of NemoClaw, which only uses Murche for its memory capabilities, and also even agentic calls goes to Murche because Murche has LLM backend. So that's another feature. So if you are interested, we are excited for that. And if you're interested for early access or to even contribute and work on the Memento, it's going to be open source, open to public, and free MIT license to use. Yeah, so that's where so this would be last page. Now I think I have some time for some questions maybe.
Thank you so much. Thanks a lot, Majid, for the overview. Very exciting things. And I have a quick question regarding the hardware that you are specifically targeting in the edge area. So can you provide us some input?
The hardware?
Yes.
Yeah, so we have a partnership with Intel specifically. That's as far as I can tell you. But our target is mostly CPU. But yeah, but we are open to collaborating with all the like edge providers.
But in the sense that actually the idea would be to target edge type of devices, like I don't know, say single board computers. Yeah. We talk about NVIDIA Jetson type of devices, right?
Yes. Yeah.
All right. Thanks. We do have a couple of questions. We can take them quickly from the audience. Danilo was asking if the storage is binary, perhaps also the computing can be kept binary and closely coupled with the memory. Then these fabrics spread across the chip through configurable connection. Does this make sense, or what are the alternatives?
Yeah. No, this is right on the point. We haven't figured out all the possibilities, but definitely if you have a binary and it's on the tip of the L3 cache, so you can use it every time to do your very quick retrieval. You just need the index, and then these all point to the actual text or actual context that is residing somewhere else. It just makes the computation and retrieval very fast, but it can be configured through other connections from the chip. Right.
Thanks. We do have a question also from David regarding the patent protection you mentioned earlier. What is it happening in this whole ecosystem?
It's basically MIP is the core of the patent. Maximally informed binary search, the compression method.
Yeah, I'm personally also quite curious to know more about the information theory based approach. I think that sounds quite interesting. But thanks a lot, Majid, for the presentation. It was great to host you here.
Thank you very much.
At the GenAI Forum. We can then move to the next speaker, David from Arduino.
Yeah.
Hello.
Hello. Hey, how's it going?
Good. How are you?
Yeah, it's fine. So I just have to like figure out how to open my slides.
Yes, can you share? I think you can. You should be able to share the screen, and then.
Yeah, that's what I'm doing. That's what I'm doing.
All right, thanks.
Now. Oh, here it is.
So it is
I just
going-
didn't know. I have a lot of windows open. That was my.
All right, I can now
Yeah.
add this.
So I think this talk is. Yeah.
Yes. No, just quickly about announcing your talk. So please just go ahead. Thanks a lot.
Yeah, thank you. So my talk is a lot more lightweight than the last couple of talks, which by the way have been very interesting to me. I'm gonna just be talking briefly about the packaging mechanism that we've built at Arduino. I'm pretty sure that some of you have already read about it. What we think is that it would be a good idea to have like maybe write a way to package physical AI software. And this is very much in line with the idea of generative AI. Since the moment we start to increase the complexity of the things we can run on edge devices, also the complexity of the kind of software that is running on different parts increases. And so we have a running proposal on how to do this, and it's running on our latest devices. So just to set the grounds, in the past, like 2 years ago, in the edge we had small models. Of course, some people were playing with Jetson Nano, but particularly in my case, I've been working a lot with the TinyML community. And the idea was to run a neural network on bare metal, using TensorFlow and some of the workflows that exist. But now we are moving into the idea that we're starting to run more complex softwares. We're starting to run generative AI at the edge. There's been people, of course, running, you say it, from Raspberry Pis to Jetson devices and everything in between. Trying to run LLMs, small versions of SLMs, and now we're coming to this new trend, new topic or new term, which is physical AI, which is basically adding physical controllers on the same device as you have the intelligence or the network. And this is not really new. If you look at automotive, for example, automotive has been having this issue of needing cars run on Linux, like electric cars run on Linux, and they typically have microcontrollers side by side with processors in order to run watchdogs and ensure that the systems are always running and always responsive, and the low-level control is done by microcontrollers. And that's kind of the space where we work at Arduino. So this is a bit the agenda for what I'm going to talk about, and I will end up making a small claim about why I think we should just collaborate and observe at least similar ways to package hybrid applications. So right now, if you're going to run a physical AI device, you're going to have concurrent models. You're going to have different algorithms that are going to be analyzing maybe computer vision and audio input, and maybe, as we say here, some policies that you have decided how things have to behave and setting up the limits and so on. There will be a layer of orchestration that's typically Python or JavaScript, not only C++. And then there's going to be low-level actuation. So there's going to be a microcontroller that will be able of running things physically, motors, low-level sensors or whatnot. And it should be able of running offline. This means that the system should be powerful enough to be able, because it's running motors or is affecting the physical space, it needs to be able of working where the connection is breaking, at least to make a safety stop. Okay, so there is the conversation right now is how to have systems that could eventually continue to operate for as long as the latest instructions are still active. And the challenge is that we have one artifact. We have one single device that has multiple layers of complexity into a single box. So the pipeline includes, on the one side, containers, where we typically put the machine learning or the language models. And they are running on the system on chip, they run on the processors, but they cannot really run on the MCUs. Then there is firmware that is going to be running on the MCUs that will be controlling the motors or whatnot. It could eventually also run small, tiny ML models that will be able of making decisions based on how communication works. And the idea that there is some level of glue, and the glue is done by this other extra software that we run in Python or whatever. So at Arduino, our first device that is capable of doing this is Arduino Uno Q. We had Linux computers before, but never following this more structured strategy towards being able of doing consciously doing AI on the edge. So this device has a microcontroller on the B side. It's an STM with a Cortex M33. So it's actually designed to run tiny ML models. And it has a pretty powerful processor. And we have a version with 2 gigabytes and a version with 4 gigabytes memory. And yeah, so the idea is that this device already implements all the things we mentioned earlier, and in a pretty small form factor. On top of that, it can have like eMCC storage, which is typically better than SD cards for devices that are running and moving and being shaken or whatnot, and we'll have the experience of running different types of devices. On top of that, we recently announced the Arduino Ventuno, who actually is much larger in size, but also much larger in capabilities. And the idea of this is to really put this in competition with existing devices. So this is, in one of the previous talks, there was a discussion about using Jetson Nano Orin. Well, this is actually better in terms of tops and better in terms of like the default memory configurations. And on top of that, it does have the low-level microcontroller. While in the picture here, we like to show the chip. By the way, this also runs with a fan. It can run without the fan, but for safety operations, we recommend running with a radiator and a fan. But this is going to be at Arduino. It's going to be like the de facto or the default hardware piece for industrial applications. And as you can see, this is the one available picture right now that I can show you. As you can see, it includes connectors for cameras and Ethernet and whatnot. So the idea is that most of the default industrial setups can be covered with just this port right away. So which is the key? One of the key pieces of software that we're running here is we have an RPC running between Linux and the MCU. We have a whole management of packages and communication back and forth. And this has been proven over the years. It's an update of a version that we had in the past on our first Linux boards some years ago. And this is very capable. So it allows you to issue, for example, Python commands directly on the processor that will be sent to the microcontroller. So it's what we call it the bridge. So how does this translate into whenever you have like a real life application? Let's say you have an Arduino Uno Q and you have a camera and the system is moving a motor, for example. I will show you later an example of this. So on the one hand, you're going to have the model that's going to be running, for example, computer vision, and you might have a web interface in order to provide the user with some UI, simple UI. This will run as different containers. And then on top of those containers, you have some orchestration software. We see this more and more running on Python, but some people run NPM, of course. And then you have the software that communicates the processor with the microcontroller. And finally, you might have a sketch or a TinyML software running on the microcontroller. As you know, in Arduino, we call sketches to the firmware, basically. So the idea is that all of these artifacts that are including some metadata that will be needed for storage and so on, should be contained into a single package. So whenever you're going to deploy your next robot, the thing that will change is maybe the sensors you add to the robot, or the actuators, or whether you have a more powerful motor, or it's a robot arm versus four-legged dog or whatever. But the whole software for your machine can be contained into a single package. This is really the proposal of this talk. And the way how we serve these packages right now to people is so what we call the Arduino App Lab, which is a local, so it runs in containers in your board, and it offers you the different models that you have available right now. I mean, you don't need this layer of user interface for most applications you're using, but I mean, if you have a prototyping equipment that we are developing multiple things, and you want to have multiple versions of things and so on, this could be a good way to try it out. It's also very important, because we obviously work a lot with Edge Impulse, that it's Edge Impulse native, which means that you can train models on Edge Impulse, and you can add them directly to this App Lab. So we already deploy software directly from Edge Impulse to our boards. So these packages, the different blocks is what we call the bricks. And the different bricks compose the apps. So you can have a brick that contains a computer vision model. You can have a brick that contains a web UI or whatever, and you just put together these bricks. You modify them to your need, and then bring in the models and compress everything together and deploy on multiple machines. And everything ends up in a single zip file. So the idea is to have, basically a package. The apps that we also call them are zip files that contain everything into a single package. So which are available models that we already offer today by default, so people can try things out and can start tinkering with things. And because as you know, at Arduino, the one thing we do is that we offer people a collection of examples just to not start completely from scratch. So we offer some generative AI examples with local LLMs and computer vision. Then we have some detection, classification, segmentation, and so on, more in depth. Sorry, I meant vision language models. I'm mixing things up. Sorry for that. We have some basic audio examples. They run really, really good, by the way, on the Ventuno, because of course has a lot more computing power. And examples for robotics and sensor fusion, which are always relevant. And so you can right now very, very easily integrate this with workflows from Edge Impulse and Qualcomm AHAP, because are the ones we collaborate with, of course. But the hardware is software agnostic. So I briefly mentioned the bricks earlier. Just this concept is one of the hardest things to understand. So I put here an example of a small functional device that you can build, and in this case, it's using information on location, and that's motion detection with an accelerometer. That information is captured and sent from the microcontroller to the processor, and then there's an algorithm there that's doing some work on it and presents things on the screen. So the bricks are containers or sketches or a piece of the RPC software or some blocks with metadata that you use to compose your house, which is your app in a sense. And here's some examples. This is an example that we presented at the Arduino Uno launch last year in October. It's a computer vision card that detects how you're tilting your head in order to operate the vehicle. Another example, these are with Arduino Ventuno. On the left, you see a robot. It's a demo robot, of course, that we did with a robot arm and a robotics platform that we built in our lab just to demonstrate how you can easily integrate the different bricks. And on the right side, you see a smart mirror that uses computer vision and some models to use some comments on what you're wearing, just to just show different integrations on, for example, a shop. So this is an ad hoc. Well, obviously, it's an ad hoc standard because we are having it for all of our products. But we think that this will be very useful for other boards that have similar capabilities. Not all boards have a microcontroller and a microprocessor on top of it. But if you have this complexity, where you have a lot of things integrated together, this idea of packaging all of the software also allows to do version control, maintenance of software, and so on, which are things that are not negligible once we have things in production. So this zip, which is the app, should contain a manifest file, the models, Python scripts, the containers themselves, the configuration for the microcontroller, and some metadata that is needed for running the system. So yeah, this is a bit of a repetition of things I said earlier, but I guess you can get the idea. And so we really would like to see this becoming an open standard. The software is open source and it's available already and runs on the board, so you can just take it and use it and modify it. We believe that the SOC plus MCU combo is here to stay. So this is not just Arduino doing it. Obviously, I think we will be the ones that probably will be selling the most in the beginning, but we believe that it's going to be becoming a standard. But we also believe that right now nobody's solving the full problem for physical AI for the packaging, and this will be a very interesting approach, and it will be interesting to discuss with people how to include other MCUs and how to open up the possibility of having different configurations and how this could work together. Okay, I think this was my last slide. So let's build this together if you're interested. That was my presentation.
Thank you so much. Thanks a lot, David. So we have a couple of questions. Still Danilo asking first, Ventuno-Q looks a great platform for VLA. What ecosystem a developer can start using?
Well, as I said, the two that we have currently running is Edge Impulse and Qualcomm AI Hub. I wonder if this answers your question. Right?
We can. There is also another question still from Danilo. What if I pick up a VLA from Hugging Face and customizing a bit? How to integrate efficiently on Ventuno-Q using both the NPU and STM32?
Yeah, that's a really good question. We have to. I don't think we have an example with this right now, but I can imagine that these examples will be crafted in our tutorials very soon, because it's an obvious case. It's like it's a lot of Hugging Face models running around that could be interesting and it could be fitting. I could also say obviously this is no secret. We actually applied for a very large European project. Probably some people in the call also applied for a similar project. We went together with Capgemini and Siemens and other large corporations in Europe. And the idea is to actually be able to bring in models that, for example, met ETH and run them on the Ventuno. So we are looking at exemplifying many different ways to creating models, synthesizing, simplifying the models to fit in 16 gigabytes and running them. And also doing a lot of cloud and edge orchestration. So we believe that this kind of device that has more memory should be able of eventually going offline, do some tasks offline, and then go online again, exchange with the cloud, update the model, or similar operations. And for that, we need to be able of running models from different people, not just the ones we create with our workflows. So yeah, so this will be documented.
Thank you. Thanks. Can you? I think we have some connectivity issue with David. I had just one.
Okay.
Hello.
Yeah, hello. I could hear you all along, so I don't know if you had problems with me, but I could hear you all along. Yeah.
Okay. Yeah, I think we have some issue with David, so perhaps we can. Yeah, it's not on my end, right, Rosina?
No, I don't think it's yeah, it's all good, Roberto.
All right.
And
okay.
yeah, you can continue with our next
Yes, we can continue. Then I will ask my question to David offline. So next speaker is Eric. Hello, Eric from Alif Semiconductor, and also Anthony from Gravity. Who is going to present?
We're going to tag team this one. I'm going to start, and I'm going to pass it to Anthony, but I'll be driving the slides.
All right, perfect. So Eric, just feel free to share the slides, and you can start and go ahead. You can go ahead with your presentation.
Yes, let me just get my slides up. I think you should be able to see them now.
Perfect. Thanks a lot.
All right.
Let's go ahead.
Fantastic. So we're going to talk a little bit about an actual Edge AI application deployment that we partnered with Gravity on for a while now. It was really Gravity's idea from the beginning, so not going to try to steal Anthony's thunder here, but I wanted to set the stage a little bit before we get into the specific use case and how that was realized. And I want to do that by talking a little bit about what Aleph is doing in the market and what kind of devices it is that we provide to people that want to work with Edge AI applications. So we were founded because we saw an opportunity to create essentially better microcontroller products, microcontrollers that, besides doing all the things that microcontrollers traditionally can do, also would have the ability to run Edge AI workloads, or you run AI workloads locally. When we were working on this, Edge AI wasn't really something that was widely talked about. There was this concept of TinyML, when people translated models to C code and ran them on small microcontrollers, and saw that this can actually work. We wanted to essentially take that a step further. We wanted to go beyond just deploying the basic use cases on these edge devices. This is kind of what the landscape of Edge AI looked like when we set up our first device families for the market. You had your typical 32-bit microcontrollers that, through TinyML type conversions of models to C code, could perform some basic use cases, basic keyword spotting, some predictive maintenance type use cases like vibration analysis, things like that. And then, of course, on the other end of the spectrum, you have the purpose-built CPUs for running AI inference and GPU processors and things like that. They could run all the use cases, very high resolution image analysis, very high frame rates, deep vocabulary when it comes to working with audio. But there was a big gap in between these two kind of types of deployments. And that's what we wanted to focus on. We wanted to try to fill that gap and enable microcontrollers that are battery powered to perform more tasks than these basic use cases. We wanted to enable proper object detection, biometric ID use cases like facial recognition, to be able to do real image classification, work with gesture identification, and also work with speech, because being able to interact with devices using your voice was already, at that time, we were founded in 2019, so it was quite a few years ago, but that was becoming sort of the norm. People wanted to be able to talk to their electronic devices. So we saw this as a very underserved area in terms of what can be realized with use cases. We wanted to try to fill this gap and deliver families of microcontrollers that are very capable, able to kind of match the power spec of the traditional MCUs so that you can run them on small batteries and maintain those type of price points while elevating the capability of what you can do with those kinds of systems. In addition to the AI workloads, what we've done with our products is we have created an architecture that is able to provide power efficient processing along the entire duty cycle of the application. Traditionally, microcontrollers save power by going into a sleep mode, and then they wake up, and then when they're awake, they process data. They do all of the things that they're designed to do. But we wanted to see if we could come up with a better way to provide some balance so that even while you're running, while you're in what we call the data collecting phase of your duty cycle, we can do that in a power efficient manner. So we can provide, a sleep state that saves you a ton of power. And then when you're just reading data from your sensors and preparing that to be processed by your neural networks, you can also do that very power efficiently. And then once you've identified the correct trigger that you were looking for in your system, we provided a high performance region of our microcontrollers implemented with different silicon gate technology that can run, a lot faster. It runs a little bit hotter, runs a little bit, higher power when you have that high performance region active. But the benefit is really that you finish the work very, very quickly when you activate the performance region, and that means that you can go to sleep faster. So essentially ingest data in a power efficient manner on the efficiency side, and then once you have discovered the trigger that you were looking for, process that very fast on the performance side of the chip so that you can quickly finish your job and go to sleep sooner. We've been working with a lot of partners during our journey. Grovity is an important partner in our ecosystem, and we've been talking to them for quite some time about use cases that the type of technology that we provide to the market can essentially enable for embedded devices that would make it possible to migrate the AI model from the cloud and run that 100% locally without even being connected to a network at all, and have essentially all the information be processed and generated locally. So for the remainder of this talk, I want to hand over to Anthony, who is going to describe this device pilot use case that we've been collaborating on, which is essentially a voice UI runtime that can provide contextual help and device control using a very deterministic retrieval system trained on documentation that is very appropriate for the specific use case, and also live information connected from the device. I've added a link to a YouTube video on this slide here. I assume that we will be sharing the slides. You'll actually be able to see the system in action too. So Anthony, why don't you take over and go through the system a little bit?
Sure, yeah, thank you, Henrik. Yeah, so take it from here. So at Grovity, we specialize in AGI voice technology and application development. So we built our own voice UI runtime. We call it Device Pilot, and I'm going to tell you more about this. So whenever we deal with embedded system and complex consumer products, robots today, we constantly encounter problems with the operation, understanding their current status, and interpreting error codes. So we figure out the list, of common obstacles, and here is this list. So you can experience, long, complex manuals, overloaded menus, unclear indicators, and sometimes you have a high cost of making the wrong action, operating the device, and all this leads us to support and service problems. So we believe, next please, yeah, next slide, Henrik. Yeah, so we believe that on-device natural voice UI layer is needed that will connect user and device, and it will be limited by predefined knowledge domain, such as manuals or guides, and this layer should be constrained by specific domain knowledge. It should be deterministically tested and formally validated. It shouldn't inherit any typical, hallucinations, risks of generative system, and can be safely deployed in mass market devices. And the main thing, it should not depend on the cloud. So existing solutions are good, but we consider them not to be the best option, Of course, we have now the commons-only voice system. So they have a weak user experience, low flexibility, and high sensitivity to phrasing, of course. On the other hand, we have cloud LLM assistants. They are massive, solid, but they experience some problems with latency, privacy risks, and And of course, they are network dependent, and as they are generative, you can experience some hallucinations from them. So we think that on-device assistance with a deterministic behavior should be a good approach. So that means that we do not require user to speak in a rigid common templates, but we also don't allow the runtime to invent answers generatively, yes, and we operate within a specific domain and we rely only on pre-approved domain content. So what tasks we consider our device pilot should execute? So we think that it can do the following things. It can, of course, respond to user questions around operation manuals and guides. Then give the user reports on device status. Then execute voice commands and guide the user through the multi-steps instructions. So the core principles which we leverage on device pilot is it should be deterministic, no hallucinations. It should be extractive, so grounded in trusted domain data, safe, so controlled execution, no guesswork, and it should be offline, totally on device, no cloud dependency. So let's now talk about what we've got right now. So we completed MVP of our on-device pilot voice runtime for specific domains, which interprets spoken requests. It retrieves approved answers from a trusted knowledge base. It separates information, intents from device commands, and it safely executes only permitted actions on the device. It's important to understand that our product, MVP, it's not a general purpose voice chatbot on the open domain AI assistant, of course. On the other hand, it's not a simple keyword spotting because it uses hybrid retrieval. And also, it's not a plug-and-play self-service system yet, but I will speak a little bit later about that. So let's look on the runtime components. The first one is, of course, speech-to-text, which is based on convolutional model optimized for deterministic low-latency execution, and it's a convolutional network with 19 million parameters. So the main, it's very robust to real. We made it robust to real-world noise because, of course, while operating, we should denoise some running water, ventilation, all this kind of stuff. So the main idea of this model, of course, is to take sound from mic and transform it into text. On next stage, we use keyword retrieval engine that performs three main actions. So first one is error correction. So we correct everything, any errors caused on the previous step with the speech-to-text engine. Next, is intent router. So it just separates Q&A requests from device commands. And the final step is hybrid search, where the system gets the response and then process it to the next stage. But before we'll go to the next stage, let's talk about this processing sequence on the next slide. So the sequence is that ISR, so automatic speech recognition, converts speech into text. Then it goes to ISR corrector, which fixes common recognition errors, domain distortions, critical term substitutions, all this kind of stuff. Then it goes to safety net that stabilizes the input and filters output part of risky, malformed, noisy cases. Then it goes to search engine, which performs deterministic retrieval against the specific knowledge domain. Then intent filter that separates a valid in-domain request from an out-of-domain request or irrelevant ones. Then bypass logic that routes clearly identified high-confidence commands into the action path. And disambiguation that returns candidate results when the runtime is not allowed to safely select a single result. So at the end of the day, runtime gives us three possible outcomes. It's exact response, exact answer, or it can be candidate list, or it will be a safe action. So our runtime leverages on Olive hardware, and what is nice of this hardware is we can use multi-core configuration here, and we use it. So we use energy efficient and performance cores, both M55 and U55. And leveraging this, we can get the best balance of performance and power consumption. So the final component is, of course, text-to-speech. So that's engine that takes the response from the previous one, from the hybrid retrieval engine, and converts text using text processor, then spectrogram generator, and vocoder into waveform, which is sent to user as a response. So, and on the next slide, you can see the entire runtime pipeline execution from a hardware utilization perspective. So you can observe how runtime components leverage M55 and U55 cores to achieve the best balance between performance and power consumption, as I said, and how this works on each step to get the right response to the user. So I think that's the last one slide showing how all this works. I think I should add that we see a lot of application areas for this case. So as Henrik mentioned, you can watch the video on YouTube. There is a use case with the washing machine manuals and guides, but we also have several use cases which we will publish. We are going to publish next weeks. Everything is about consumer electronics. So the potential areas are consumer electronics, white appliance, robotics, automotive, this kind of stuff, where we face real problems with these huge manuals. And from the technological point of view, our next step will be we are going to make adding new domain knowledge automated. So it will be automated procedure when we can upload PDFs and add some languages, and that will transform the runtime into some kind of a platform. Thank you.
Yeah, I think it's really interesting to see the realization of this, to put together essentially a complete system that is able to parse natural language and essentially look up the correct answers to questions that have been identified, and then also speak them back to the user and have that contained in a single chip solution, essentially, that can then be essentially integrated in any type of system that requires some knowledge or some understanding to operate, and make it into something that sort of just naturally can interact with the user or the operator of the system. So it's very satisfying for me that I've been watching the development of Edge AI now for a couple of years to see, how these use cases that have been discussed and kind of theorized about for a while now actually coming together in especially the kind of microcontroller class of devices, because obviously this is things that can be done cloud side since there's really no constraints in those environments, but to see it realized in an embedded system, I think it's very promising. So that's what we wanted to share today.
Thank you so much. Thanks a lot, Enrique. Yeah, indeed, quite impressive the fact that we are able to do all of this in a microcontroller. We have a question from Danilo, who is asking, from model lifecycle maintenance, intrusion resilient, and upgrading standpoints, how do you see a modular multi-stage audio workload versus a monolithic end-to-end deeply optimized approach? I don't know who wants to answer.
I think I will take that one. Oh, it's a very good question, but what should I say? I should say that monolithic end-to-end and deeply optimized construction, it seems to be a good option. But the problem is that our resources are limited, especially on microcontrollers, especially in the means of memory. And as long as we go deeper and deeper with deep optimized solutions and models, the memory consumption becomes so huge. So you should also always look for the balance. And nowadays, of course, you should always look for make it cheaper for the potential customer, for the final customer. So I would say that I like the modular constructions because I can, if I have some restrictions on memory or resources, I can take out some of the modules. Maybe the result, the accuracy will go down, but still it can be a good one for the resources that I have on the hardware and the customer wants to pay.
I think another comment that can be made just in general when you're kind of comparing these approaches is that for these very constrained devices, being able to break up the system into modular pieces and do some works on them individually rather than as a unit usually leads to essentially better long-term power efficiency, because when I'm deploying updated, improved versions of the system, if I don't have to replace the entire system every time, essentially that means I don't have to keep my radio turned on to push an entire firmware. I can just push pieces of that firmware into the system as they get improved. Usually the most expensive piece of a duty cycle when it comes to power consumption for an embedded device is when the radio is on and transmitting and receiving. So the more you can keep that transmission to a minimum, the longer your battery will last and the happier the end user gets.
Yeah, thanks a lot. I have a small question. Anthony, you were mentioning quickly during the presentation that, of course, you've been trying to develop the system in such a way that it's kind of resilient as much as possible, respect difficult environments. I'm just curious to know whether there is some specific noisy environment or some specific acoustic condition that is really challenging your system and in which you really need to do some extra work for optimize it further.
Yeah, I think the most challenging is getting a lot of echo. So when you have just some noise from running water or from engines or from pumps, it's not so challenging to reduce the noise from them. But when you have echo, so the room, with a lot of echo, yeah. So that becomes challenging. I think that's one of the cases we don't like, but still we cope with that and it works.
And very quickly, you hinted about the different use cases. Can you tell us a bit more? I mean, a couple of examples on where do you see this kind of application flourishing, for example? I know that more is coming soon, but if you can give us some teaser.
I have a lot in mind, but I think what is interesting to me and what seems to be interesting to the market. Yeah, there are two differences. What I think is interesting,
yeah,
what is market
of course, good point.
So we are preparing demo for laptops, and we are preparing demo for automotive, and one more domain which I like. I just like it. It's something about. It should be about the yachts.
Oh, okay.
Yeah, yeah. So yachts, they have a lot of different subsystems, and the manual for example, for your car, you have manual which is that thick, and for you to have that one. So that can be a good case.
Yeah. This sounds interesting indeed. All right. Thank you so much, Henrik, Anthony, for the presentation. I think this was a great example of overlapping areas with hardware, software, AI, and I think this was very, very insightful. Thank you so much again, both of you. Thanks a lot.
Thank you.
So we can then move to the next and last but not least speaker of the day, Marcus from Forest Hub AI. Hello, Marcus. How are you?
Hi, Roberto. Yeah, nice to see you again from San Diego.
Yeah, nice to see you again. Yeah, we met a few weeks ago in San Diego during the summit.
I'm fine. You?
Yeah, pretty well, pretty well. Looking forward to hear from you. So whenever you want, you can start with sharing the slides.
Great.
I think we can. All right.
Okay,
yes.
Great. Now you should see my screen.
Yes, we can see it, and it's presentation mode. Thanks.
Good. Yeah. Thank you for having me. Today I want to talk about a use case we developed, and maybe this is interesting for some people too, how we make this, and what is important in this use case, and what is possible really with agentic AI on the edge devices. And this use case we have is the intelligent service technician for industrial machines. And yeah, I'm Marcus. I'm the founder of Forest Hub AI. And yes, so let's jump directly into the problem. So the normal systems we have, the embedded systems or systems at all, they are most of the time really static. So we have in the meantime, we have increasing complexity in the system. So we produce even more complex parts in the world in the manufacturing process. So we have even more modern machines when we look over what we are producing, getting even more and more complex. And we have more complex mechanics, more complex electronics, firmware, and so on. And the knowledge often is really distributed in the different kind of systems we have. And when we come to the machinery, even more distributed, because we have one company, for example, is building the machine, the other one is using it, and then we have the knowledge distributed in different heads and in different companies or different systems. And when it comes often to AI in the machinery, we have, for example, something like anomaly detection, or we have something like predictive maintenance, but we do not really have an interpretation layer in the moment. So the systems are executing, but they don't understand what they're doing. And this is the cool thing. So when we have now from the normal embedded system, which are really reactive, rule-bound and signal-driven, we can now have a shift with the agentic to really context-aware systems and decision-capable systems. They are interactive and adaptive. And so with the capability of agent, the embedded systems can have these features of the agents too. What an embedded agent is, I think everybody who's listening here is already a pro in this topic, but only to make it short. An embedded agent is an AI agent which runs on embedded systems, of course. And here the main points are, it's of course it could work on device, where the agent is really full on device in the best case, with no connection to the cloud, for example. And it's have the capability of real time, whatever real time means. This is a little fuzzy word, of course. It had access to its environment, so for example, the sensor data of a machine or the system state, and of course the operational context. And it's capable of doing actions, the reasoning, decision making, or it can execute some actions. Yeah, and it's not replacing the normal logic; it's augmenting it. And this use case I will show you now is built on our platform, the Forest Hub, where you can, where we want to use help you to handle the whole life cycle of an agent. So first of all, of course, the building of an agent, where we have a no-code platform where you can build your agent, then of course deploy your agent on different devices, where you can orchestrate agents over some protocols, and of course doing when it's running in the field, doing the agent ops. And what our platform is, and or how the architecture, or what the architecture of an embedded agent is you can see here. So in a normal edge or embedded agent, we have the input data, which could be, for example, sensors or documentation of the context we need for the agent. Then, of course, actuators or the tools they can use. This can be, for example, motor, pump, or whatever. What could be an actuator. Then we have the agent itself with all the memory, reasoning, and so on. And then the SLM, which is, it depends. Is it working on device when the device is big enough? We just heard really cool talks from Arduino and ST and NXP, what is even possible on the devices, so then can it work fully on device? And then, of course, the data sources for other data we need. Is it native data, like I said, documentation, or the data in the cloud when we have a connection? Yes, and now let's really jump into this use case. So imagine we have an industrial machine where we have all this distributed knowledge. We have the sensor data on the machine. We have the system states, which is in the machine, and the documentation, which is somewhere else. So most maybe on the manufacturer of the or the machine builder, or somewhere else in the cloud or on the computers of the development team. And with agents, you can bring all this information now together to have really the understanding of what is happening in the machine. So not that, and this is the shift from that the machine not only do what it should do, so produce whatever you want to produce, for example, mechanical devices or textile or chemical, whatever. So now we have really we can talk with our machine like with our normal service technician. So in the most cases, when the machine operator, for example, is in the machine and an error appears, then he needs to call the machine builder. Then he needs to drive with a service technician to the machine. He needs to have a look. Maybe he reads some data, make some test drive, and then he know what to do and repair the machine. And with now all the context information on the machine operator can help himself. So he can ask the machine, for example, hey, what's your problem? And the agent on the device, he reads the sensor data, he reads the documentation, the E-plan, for example, and see, okay, the data on the sensor XY, whatever, looks a little bit strange. He looks in the E-plan, where is it connected, and then get really an image of what is happening. And then he can say, okay, do step 1, 2, 3, and then it works again. So this is the use case, and how we was doing this is in a layered system, and where we can now integrate the agentic layer to make this happen. So of course we have our physical layer with the sensors and actuators, which is normally provided by the machine builder. Then the OEMs, then of course we have our embedded runtime. Most of the machine builders have their own have an operating system on the controller. For example, when Siemens or when it's Bosch Rexroth or whatever device they use, they most come with such an operating system. Then of course they have the system interface layer for the event bus you need in the machine industry with the data access, APIs on the machine and outside. And then we are building this agent layer inside on top of this layer. So we have the access to the physical layers over the other layers. Then we have access to the data and bring all this information together. And then, of course, the communication outside, or optional communication up to the cloud, where we can even make more powerful systems or agents. And with bringing this all together, like I told you, we have now the capabilities to really bring the reasoning, or really bring this. We can do. We can see the reason why something is happening, for example, over the state, when we put it to the agent and make a decision what should be happen next. And then we can or the agent can act, for example, make test runs on the actuators. And so we have, some key design principles when doing the use case. Of course, the separation of concerns. So we do not rebuild the logic of the machine when it's producing something. We want to go on top on this and bring the knowledge or the context of the knowledge inside the machine to make it even better. Of course, an on-device first, because I learned a lot of machine manufacturers don't have a cloud connection really on the device. So this was for our customer, it was really important to have everything fully local. Only when the customer wants that a hybrid mode is possible, so he can read out the states of the agent, but it should be work local first. And of course, resource aware, because the IPCs most of the time on the are that big and have the big computational power. Yeah, and what this architecture enables, I already showed you. So now you can talk with the machine really easy and can say, why is the actuator not responding? Why is there a problem? Why is it broken? And the system helps itself. And the next step we are doing in this project is pretty interesting too. So we give the AI agent the capability of machine learning. So we have an auto machine learning tool which is giving to the agent, so he can build his own anomaly detection and get better over the time. And when the anomaly detection is done, you can make this a step further and say, okay, now make your own predictive maintenance model, because he's collecting the data all the time, and because he knows the context of the sensor data, what is happening of the machine, he can build on device his own model for the time series data to make even more better, or to make it able to have predictions from the agent itself. Yeah, and this was my presentation about this use case. If you have any questions, please feel free to ask. And yeah, thank you very much for listening.
Thank you so much. Thanks a lot, Marcus. Well, we have had several discussions during the past few weeks about this very interesting area. It's also an area where I'm currently working on as well. I have a couple of questions for you, but let's take first the one from Danilo, who is asking, what are the strategies to make the agent self-aware of the consequences of any action is going to take? And maybe being aware of this could change its mind and take other routes?
Yeah, a really good question, which is always an important question when it comes to physical AI, because we handle physical devices with it. And when we look at a machine, there can happen really bad things when the agent is out of the control. So in our use case, we make this over an improvement system. So every really hardware action is needed to be approved from the operator. So it can write the execution order, but to allow it, the operator needs to say, okay, let's do this operation task. This is one method. The other method is to have an governance agent. We tell this like this. So we have an agent which is only there for governance reason, and look what the other agent is doing. For example, this is a more autonomous method, but I would say human in the loop is in the meantime the most safe, but there are different kinds of types you can choose to make it fully automatic. I hope this answered a little bit the question.
Thank you, Marcus. So when it comes to my question, I think this is a very interesting area, because we are really talking about a distributed system and how to put different pieces together. And I think what I perceive from your presentation and the approach that you're having with your work is the fact that somehow we are not forgetting about, let's say, pre-generative AI applications, right? You mentioned about the opportunity to build application like normal machine learning models, time series, et cetera, et cetera. I think this is very important. But when it comes to the system perspective, for example, the orchestration, then we need to deal with the heterogeneity for example, of the different devices. So you have very constrained devices like embedded system, more resourceful devices, and we discussed over the past few weeks, also in San Diego, that one critical aspect perhaps will be the need of bringing similar MCP or A2A type of protocol also into the embedded scenario. But what's the biggest challenge that you envision for doing this? Just to give you additional context, before David from Arduino was mentioning the need of having similar tools like OCI for container, for having similar way to describe an application, etc., etc. But this is, of course, never trivial. You need to put, you need to essentially make some sort of standardization effort. From the practical point of view, what do you think is the biggest challenge?
Yeah, this is a really good point. And I think the direction need to go in such kind of standardization in really every field a little bit. Of course, we need an exchange format to exchange the models. Nowadays, we have ONNX, which is pretty well and good used. And I think when it comes to communication, like you said, that we will have this problem. A small microcontroller execute his calculation really slow, a small one really fast, or when it comes to the cloud, then we have, for example, some lag around the communication, and this need to be handled. And then we need for this protocols to can handle this, algorithm who can handle this, and some standardization to make this happen. Really interesting in this field is, to be honest, when it comes to the agent research, everybody was jumping to MCP, for example, and nowadays we say, okay, MCP is pretty cool and working good, but CLI when it comes to normal tasks is even better, and CLI is super old technique, but agent can handle CLI better than MCP, is more efficient. And I think, there need to be some more thoughts about what is really efficient for agent and what is working well and give all the context an agent needs. But I think communication will be a problem when it comes to physical AI and to robotic in the future.
Yeah, thanks, Marcus. Yeah, I think this is critical aspect, and welcome back, Danilo. And also Danilo yesterday was mentioning during his presentation that a big effort is required in terms of standardization, for example, for interfaces. And I guess that one of the next phases for agentic AI, even at the edge, and especially at the edge where we are dealing with a lot of heterogeneity, it's a really necessary step. Danilo, do you have a question for Marcus? Another question.
Hi, Marcus. Glad to see you again. No, I think you elaborated quite well the topics. Certainly, the self-awareness of the agents is something quite important. It's a kind of self-safety that maybe is a feature and is an important feature.
Yes, indeed. Glad to see you too, like always. And like I said, I think this is a problem every agent have. Nevertheless, it's physical AI or it's in the cloud or whatever. When it comes to really big company agentic AI, they have the same problem. And I think it's not the super solution in the moment, but I hope the research is going on.
Very good.
Thanks a lot again, Marcus, for your contribution. Very appreciated. Thanks a lot.
Thank you very much.
Thank you. Thanks.
Ciao, Marcus. Ciao.
So, Danilo, here we are.
First of all,
very busy days. Very inspiring.
First of all, Roberto, thanks a lot. You did a great job in moderating all the contributions. really grateful for that. If I may say a few things, yes, all the speakers were great. The subject were at the right level for the community. I think we got a full set of the update from all the speakers. There are a few things that touched my mind. Certainly, conversational AI with audio is a low-hanging fruit, and this has been confirmed by Davis and by also Enrique. And I'm super excited to see that space application are entering into the picture. This is I'm a fan of space
I was sure
applications.
about it, indeed.
And I hope this will be expanded in the near future. I was so happy to see a company, Godel Space, to start sharing a few things that we as a community should consider. But overall, all the discussion were very, very productive. And thanks again to moderate that.
Yeah, very, very insightful. And if we want to, so during the last forum in November, we were kind of envisioning a few topics that perhaps would have been more present in the next forum, like for example RAG, and we had some RAG, much more than in the previous forum. We have had physical AI, and even we went to space, right? What do you envision for the next one? So what is going to be? I mean, the field is evolving so rapidly that it's very hard to keep the pace. But what's your take on this?
It's going to be a challenge, but maybe a high level topic that is spinning in my mind is really what kind of optimizations and let's say facilities also in terms of APIs can we offer to ease the life of the developer. For example, I saw this new platform from Arduino, the 21Q. I think is a great platform, is a perfect example of how different systems can coexist. Traditional TiNML type of processor with advanced processor, certainly more suitable for physical AI. So really, this is the type of things which could be a great input for the developers. A good start, not enough, I think. In fact, David said that for the moment there are no examples, but that means that maybe next time there will be, and everybody will work in this direction. And I think this is something that I would like to see the next time. But you know, things changes, so
absolutely.
I'm sure other topics will pop up.
Yeah, and I think, for example, one shift that perhaps we start to observe today is the kind of little by little the increasing usage of these alternative models. I mean, alternative to transformers, for example. That could be, especially for the edge, a very big opportunity. Of course, there we really need to understand what are the different trade-offs in terms also of the quality that you can get from this type of models, but that also looks promising. And I also would like to connect to the last comment and a question you asked to Marcus, respect the awareness of the agent and who is responsible for the decision of the agent. I think that part is going to be extremely relevant also for the edge, where perhaps you might expect that because of the limited capabilities of the devices, these kind of failures or unexpected behaviors might appear in a much more frequent fashion compared to cloud-based approaches. So I think these different areas are also, in my opinion, something that I'm sure we are going to see during the next or in the next few Gen AI forum.
And yes, I was also glad about the comments from Alif Semiconductor when I apologize, I don't remember the name, but the person said, the speaker said that a modular approach maybe is a good fit for a low-cost platform. So a modular approach means also interfaces, and because people really from one side is see a lot of new models coming from Hugging Faces and would like to take advantage of them and then mix and match. And so a modular approach is the way to go. This I agree, totally agree. And in fact, I'm happy about this comment, which is coming from a well-reputed company. And if we couple this with the other proposition from the other speaker, we see that there are common needs start to appear, and maybe working on that, the next update will be certainly exciting.
Yeah, and we look forward to the next forum and what comes next. So we almost reached the 3 hours today. So despite we had fewer talks today, but still very dense and interesting discussion. So I think it's time to wrap up, right, Danilo?
Yeah, no stops.
Yeah, indeed.
Without any pause. So huge thanks to you, Roberto, to Rosina,
thanks,
to the
Danilo.
AGI
Thanks
Foundation
to Rosina and everyone.
And the AGI Foundation, because without such a community, these things could not happen. And so my very deepest gratitude. And see you next time.
See you next time.